under the glass of a frozen sea. A secret stirs where no eyes can see, like whispers trapped in a crystal tomb. Europa hums its ancient tune. I think of our stuck buried deep, a lake that dreams but cannot sleep. What waits below? What breeze? What hides in the heart of ice, where time collides? Signals flash like ghostly flares, answers tangled in cold threads. Beneath the ice of Europa, life sings soft like a distant nova. Are they monsters or are they kin? Do they fear us or let us in? Beneath the ice of Europa, life sings soft like a distant nova. Are they monsters or are they kin? Do they fear us or let us in? Wheels pierce down, machines hum low, to touch the past, to learn to know. A glimmer, a movement, a fleeting trace, a trembling hand, a foreign I think of explorers long ago who chipped at secrets locked in snow. They found life where none should be, a mirror of us beneath the sea. A canvas black with whispers gold, stories untold, secrets unfold, diamonds scatter where the shadows sleep, infinite skies, a promise to keep, beyond the lights where the stars collide.
Hey, welcome everybody. Welcome to Skytour Livestream. It is a beautiful Wednesday night here in Connecticut, except for all the rain and the clouds. Daisy and Zoe were talking about rain, and it's a beautiful day out in the desert, as you can see from there, the beautiful blue sky in that top view. That's just beautiful out there, and we're gonna be exploring that tonight. Give ourselves some time, right? It should be fun. So I'm glad you guys are here, and I'm ready to jump in. As you notice, it's not quite dark out there, but that's okay because we can still see things. As you see, look how bright it is up here. Okay, you see how bright it is right here. Let me just get up here. You see how bright it is up there, the sky. But look at, we can still see star clusters because we can isolate them and see them. Now, you can't see any stars in the sky with your eye if you're out there, but our telescope knows where it's looking, right? So we can see them. Oh, yeah. So that's cool. So I have to say hi to folks that are here. Star Panda, good to see you as always. How are you, hon? And we have Jack Mick Astrophoto. Excellent. How you doing? How you doing, brother? And Good Vibes. How you doing? I just talked to Good Vibes a little while ago in other messages. I think you sent me that beautiful photo of the water. And then Lori at LDP. How you doing, Lori? Good to see you. Tony Lowe's with us. And Immortal Sergeant had to run to work, but thank you for checking in and saying hi. Daisy and Zoe, good to see you. They got lightning storms down there. I hope you don't lose power, guys, but we probably don't. You probably won't. Okay, and then we have Donald Kunzers with us. And Sean Paris. How you doing, Sean? Nice to see you as well. So this is the early crowd. You guys are the diehards that come in. So we're going to do some nice things, check out some nice things for you tonight, and make it a night worth remembering, I hope. We've got galaxies to look at. We've got other things to look at. And I've got my screens like this, so I'm going to be looking here. This is my large observatory feed here, and then over here on this side is the broadcast screen. So I'm going to be kind of looking at both places. So if you see me looking out there, I'm actually looking at this right here, the same thing you're seeing on this side. I know, weird, but that's how it works. And then if I go out of focus like that, well, it's because my eyes aren't focused. Let me see if I can fix that. Okay, so it'll get me back here in just a minute. Yeah, I just had to see that. I don't know why it does that once in a while. Anyway, guys, again, thanks for joining us tonight. And I would like to mention that the song you heard at the very beginning, very beginning, Dreams of Europa, that's on our album called Rising. And it's free to the album. It actually has like 10 songs on it. Free to any of the paid Patreon members. Okay. So I'm very, very happy to make that available to you as a link that I'll put on the website, on the portal at skytourlive.org. I'll probably get to that tomorrow. But I want to just make sure that you knew that's a free album of our music that we put together. I wrote all the songs and arranged and composed, blah, blah, blah. But, it's just a beautiful add-on, and I'm not going to charge money for that. That's a freebie for you. Eventually, maybe we'll charge, but you know what? Now, nah. They're beautiful songs, so why not share them? Anyway, I want to say hi to Shelley Gormley, who joined us. She's from Canada in the house, she says. That's wonderful. And so that's cool. Now, you may wonder what this is we're looking at right here. And I'll just annotate it for you so the telescope knows where it's looking. It's looking at a cluster called Messier 41. What's that? Messier 41 is a cluster that is right down below Sirius. Here is the big dog, Sirius. Okay, there it is right there. Oof. Okay, it's actually a greyhound because those are Egyptian hunting dogs. So Canis Major and Canis Minor, Sirius and Procyon are their names. Those were greyhounds. I had a pair of greyhounds, and if I had thought, I would have named them Sirius and Procyon, but I named them Tycho and Kepler. Not bad, not bad. So that said, we have Sirius here. We have Orion over here. You'll notice Orion's up here. Orion is right now right on the southern meridian. It's the line that goes straight down to the south. Okay, it's almost on it. It's just a little past it. Okay, this is the line. All right, so Orion's just past the meridian, and as it gets darker, we might check some things out there like we did last time. But there's other things to look at down here which we're going to check out. So that's going to be kind of fun. And we'll get to that as well. Now, Donald Kunzer says, someone's driving up the observatory. I thought it was lightning. No, actually, you watch the telescope cameras convert over to night mode where they went into the infrared only. The only camera that can see the road is this one here. Okay, the one directly above here. And I have it aimed right now at the telescope. But if I want, what I can do, I'll show you. If you just keep looking at that image, I'm going to move it. Okay, and I'm moving the camera out so it's looking out here. And you can see that you can just barely see the ground here. You see the other big observatory dome up there on the top of the screen, and you can see the western horizon, getting darker as we get our sunlight down. That is the infrared illuminator that you're looking at there, that light. That's not an actual light on. If you're in there, it's pitch black to your eye. Okay, and that's the illuminator lighting up this view. This camera's illuminator is off because we have other people that are doing astronomy on the mountain with us. There's 10 other astronomers on there with me, and this is one of those conditions where you don't use infrared light because it will interrupt and get in the way of other people's sensitive sensors that they might be using. Karen Belmont's with us. Hey, Karen. Yes, this is in fact a live broadcast. Welcome to a live broadcast of SkyTour Livestream. Okay, and so let's come back here. First of all, we're gonna look at some other things up here too. There's a couple things I want to check out later. We will do this. Okay, there's our stars. What I want to do is something I haven't done yet, and that is I am going to focus the system. It actually doesn't look bad right there, but it's not quite right, so I'm going to do it one more time, and that's what I want. And then we're gonna make a 2-second shot. All right, and we're gonna start doing a focus run here. Here we are. All right, so now we're gonna go do our focusing run. And so as we do our focusing run, you'll notice that the stars will, of course, increase in number. You'll see it says right now we have 13 stars, 14 stars, and as it gets more focused, you'll see that number increase. Then it'll start decreasing, and that'll be after it reaches that peak focus position. All right. So the number we care about is this number here, these scores. The best score is the one that we want, so that it'll target the best score that it finds. And now we're at 14 stars, 15 stars, and you'll see the curve drops down as we get closer to the focus point. And it's going to make a curve down here, and then it's going to make a curve of best fit. It's going to find the lowest point of that curve, and then it's going to that'll be our focus spot. So we'll let that do that for a moment. Yeah, Donald Kunzer says getting used to daylight savings time. Yeah, no kidding. Yeah, because now all my streams have to be an hour later. Remember, they were 9 o'clock. Now they're 10 o'clock. It's 10 o'clock. Yeah, well. Kathy Messick, hi, how are you? Nice to see you. Rockstar, what's up, brother? Good to see you, man. So we'll start to see this curve go up here in a minute. Okay, we're right around the best focus spot, so this should start coming up. and this will be the dip that we're looking to manage and get. Here it comes. You can see it starting to come up, and we're at 10, and sometimes it doesn't catch it, and it just has to do with the way this sometimes works. But our curve should show up right about here. See, when it does this stuff, it kind of bobbles. It may not catch it, but I know that it's right here. So we'll do that. Oops, that's not good. There we go. Now let's see if it can figure it out. Yeah, it's doing 13 of 12. So it's going a little beyond. There, it did find it. There we go. Okay, so we're going to hit best focus now. And we're going to go back to that focal point, which is our best focal point. And we should end up seeing our stars looking really nice once this settles in. We go back to our live view of the camera instead of the focus spot. And let's see what we got. All right, let's... I'll take us to a 1 second guy right here. Let's try that. Oh, see, now that looks much better. Okay, so we're good here. So there's our stars. Check it out. All right, so this again is Messier 41. It's also called the Little Beehive. Now the Big Beehive is also up. That's in the constellation Cancer, just a little bit more to the east, and we can check that out too. You'll notice that this one kind of fits in the view. The Big Beehive, you only see a few of the main stars in here, and it's much bigger than this whole screen right here. So why don't we do that? Let's start an exposure here. Let's do just a 12-second exposure of this, and we have our gain at 100, which is close to what we call unity. It's not it's actually unity for this camera. That means the minimum amount of noise is here. Now our temperature, if you notice down here, okay, we supercool the sensor of the telescope. All right, so this one is now at minus 17.4 Celsius, and that comes in really nice, and it allows for very little noise on the actual sensor. We want to go to minus 20, but the temperature in the building is plus 23 Celsius right now. Okay, so it's kind of warm in there, and so we typically drop it 20 degrees or more below the ambient temperature if we can. And so right now we're actually a lot more than that. So we're at minus 20, heading to minus 20 at minus 17. All right. So the next thing we're going to do is, this is our guiding system. And I should be all connected. I am. That's good. And what I'll do is I'll take a guiding image and get rid of that. And now we see these stars. These are guide stars that I'm going to use. Tell it to grab a guide star. And we'll get a green circle. There we go. Say guide. Alright, so now the telescope is being micro-guided in that one little star right there. And this is the data from that star, the brightness of the star. We like seeing a nice peak that doesn't go off the view here, because that means it's saturating. Alright, so that's there, doing its thing dutifully. And now what we're going to do is we're going to do a 12-second shot that we're going to start stacking. I automatically adjust the height of the image so that it stacks, or sorry, it shrinks the image so that the live stacking window doesn't block any. Okay, now that's it. You'll say, what's that doing? What are you doing? And that's basically, I had too much processing going there, so I got rid of that. So we will color correct this, and then we're going to do a correction for the, oh, look at that. So now we're getting to see what I wanted to show you, and that is that in this cluster, okay, here's the data. It's red, yellow, and green curves. I'm sorry, red, green, and blue curves. And the white curve is the average. So we adjust our levels to that white curve. So if we come and climb that curve, but not go past it, we get our background as dark as it can get. And then this brings out any faint details. In this cluster, we don't have any. Okay. Okay, so now we do this. I want you to notice these beautiful red stars here. See these beautiful red stars? Okay. Now, those stars, I haven't checked, but I'm guessing because this is the same for other clusters. Those red stars are members of this cluster, but they're evolving faster because they are maybe slightly more massive, and so maybe they had a little bit more hydrogen, so they're more massive, so they evolve quicker. So now that is happening, what we'll find is that the clusters will start evolving off what we call the main sequence. So that is the point where the stars are all fusing hydrogen into helium like our sun is doing. And that time in its existence, all right, is very important because it's during that time that you're going to get planets that are able to form and life may be able to come about. And that's the kind of thing we're looking for in the universe, is stable stars where that can happen. Stars like our sun can be stable. And before our sun's type, we have several others. We have O, right? Very, very hot and blue. Then we have B, all right? And then we have A, and then we have F. Now, O and B are very, very blue. The O stars are the hottest and bluest in the entire universe. B are blue, but they tend to be a little more toward the white end, and then at the end. But they're mostly blue. The Pleiades are a good example of B stars. And then we have the A stars, which are whitish, okay, and those are very interesting stars because it's around those stars that we have found planets, but they're not habitable worlds. They are scorched worlds because the stars are usually very, very hot. And then F stars, just before ours, which is a G, F stars are starting to tend toward yellowish white, okay, but they're still kind of white. And the F stars are a little more massive than our sun in general, but they're also very very capable of having planets around them. But the temperatures are still just a little high. Our sun's surface temperature is 10,000 degrees Fahrenheit, for instance. The internal temperature in the center, where the fusion's going on, is it's millions of degrees, above at or above 15 million. Okay, and that's Celsius, by the way. Oh, look, a satellite went through. Can you see it? Right there. Okay, so. But the G stars, or the F stars rather, can have planets, but they're still scorching the worlds. They're still a little bit warm. So what we have is, we have stars like the G-type stars, like our sun, which we know can support planets and life. Ta-da! Here we are. Okay, and then after G, those are the stars that we look at for potential planets, and that is after G. You have the stars known as K stars, right? You have O, B, A, F, G, K. K are orangey stars, kind of yellowish orange. And then you have M after that. Now, as we go from O stars down to the M stars, they go from very large and massive down to small and diminutive. So the smallest a star can be is, you can have a star that's the size of the planet Jupiter, but it's got to be much more massive. It has to have about 80 times the mass. So if we could add 80 times the mass in hydrogen to Jupiter and crunch it all down in there, we'd get the interior so hot that it could start fusion, and we'd have another star in our solar system. That would look kind of interesting, but there's no way that's going to happen because all of that excess hydrogen is long blown away by our stellar wind and so forth, or trapped by other planets in our solar system. I have to I've got to take off the automatic hunting of that camera. There we go. So now it'll stay on there. So oops, I didn't want to do that, my mistake. But there we are. Okay, so okay, we're back here. There we go. Okay, just had to get that back. Okay. right, so we've got 27 of these. I'm going to save them. So, but here's the thing. So when we get to those M stars, you have to understand there's two flavors of all stars. You have stars that are fusing hydrogen into helium, and you have stars that aren't. Now, they all start that way. All of them, without exception. They all start by fusing hydrogen, the most plentiful element in the universe, into helium, the second most plentiful. Okay? But when they stop that process, it's because they've run out of their hydrogen in the core. It's only in the core where this is going on. The rest of the star, as I've said many times, is just along for the ride. How big is that core? 15 to 20% the size of the star. So the only thing doing fusion in our sun is a core that's about 15 to 18% the size of the sun that we see in the sky, which is half a degree in the sky. Okay? All the rest is along for the ride. But it's a hot gas held to the star by the star's gravity. So, that said, when we have a star like the sun that runs out of hydrogen, what's it going to do? Well, it's going to become a red giant like these guys. And why is that? Well, when it runs out of hydrogen, then the core is going to start to contract because there's no hydrogen. And so the pressure of the overlying layers is going to win out. And because it's fighting a constant battle, it's pushing out with the same force of gravity trying to push in. That's called hydrostatic equilibrium. But don't worry about that. Right? So this equilibrium is going to be altered when the sun and the star or a star, any star, is going to stop pushing out radiative energy. That radiative energy holds the star up against its own collapsing gravity that wants to crush it. So when the core of the star starts to collapse, when it runs out of hydrogen, then the core gets hotter. And when that happens, the whole star is starting to collapse. The core especially starting to collapse. As it gets hotter, now to the outside the core, the rest of the star sees a much more intense heat and energy coming from the center. And so that pushes the outer layers out and turns them into one of these, a red giant, like you see right here with that arrow. Okay? And that's the death knell of a star like the sun. When it goes into that red giant stage, there's no more hydrogen to fuse, so it starts to collapse in the core. It gets really hot in there and starts to push out the outer layers. Okay, because again, those are just along for the ride. So the star will go through a bunch of these processes where it gets really, really hot. It can maybe fuse carbon into nitrogen and oxygen. Okay, or fuse helium into carbon. You look in the periodic table, you go down the list, and that's the next step in the fusion process. So hydrogen makes helium, helium makes lithium, beryllium, and then carbon, nitrogen, oxygen, etc. And so a star like the sun can never really get to carbon very easily, but we might end up with enough carbon made that the sun will have had a core collapse that was hot enough to start making the carbon in the core, right? But it won't get farther than that. Bigger stars get all the way to iron, which is number 26. Okay, so that said, hopefully I didn't leave any of you in the stellar dust, but I just wanted to mention that because we're looking at stars at a few different levels of their evolution, and these red stars are at probably the same age as these stars here in the cluster, if they're in the cluster, which I think they are. However, they're more massive, so they burn through their hydrogen faster, right? So you can have a variety of stars in clusters. They're not always all the same, okay? Okay, so this is cool, and so we'll save this as M41. All right, save exactly as seen. I'll do the annotation one more time because I have a feeling you'll be able to, if I save this image with the annotations as well, then you could reference this later if you want to. Oh, that's the wrong thing. Haha, my mistake. That's what I wanted. Okay. We'll save that with the annotations. Okay. All right. So there's your little mini lecture on red giants and regular stars. Okay, and again, these spectral classes are O, B, A, F, G, K, M. Now, There was an old way that you learned how to remember that. It was OBA, fine girl, kiss me. There's no accounting for the old days. Don't judge the past by the rules of the present. All right. So, but that's how it was. And if you're a female, you can say, "Oh, be a fine guy, kiss me." I mean, the G was a G, right? Girl, guy, whatever. And that way you remember what the spectral classes are. But the type now is the interesting part. Okay. M stars, like I said, can be the size of Jupiter. But M stars can be Betelgeuse. Okay, Betelgeuse is so big that if you put it where the sun is, it'd go out to Jupiter's orbit. Okay, so how does that even happen? How does it? By the way, I just heard thunder. So just so you know, if we lose power, not my fault. Okay, so M stars can be the size of Jupiter or the size of Betelgeuse. How do we differentiate that? We differentiate it by looking at the evolution of the star. If we see that the star is fusing hydrogen into helium and it's a red M star, we know it's one of these little mini stars. But if it's already gone through its hydrogen because it's a supermassive star, then its core is gonna collapse, like I said, and the outer layers are gonna expand. And as they expand, they get cooler because they're farther from that hot center. And as they get cooler, you're inevitably gonna get them to look red. Okay, like this. Okay, so what we look for is whether the star is actually showing signs in its spectra that it's fusing other elements. And if it is, then we know it's one of these gigantic stars. And that means it's one of those supergiant stars, because the OBAFGKM is just about temperature. Okay? O, bright blue. M, dim red. Okay? Or just red and cool. All right, so the size of the star dictates how bright it's going to be, and that size is related to its evolutionary state. So, for instance, we call stars like the sun that are fusing hydrogen into helium normally, we call them dwarfs. Believe it or not, dwarfs. 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 The sun is 865,000 miles across. Hardly what we would call a dwarf, right? But it is, in the cosmic scale of things, it's what we're calling a dwarf. Now, when the sun swells into a red giant, well, then it's going to be a star that might be a star like well, it won't be called a dwarf. It'll be called a giant or a subgiant. And those have Roman numerals. The Roman numeral for the dwarf is a V, a Roman numeral 5. The Roman numeral 2, Roman numeral 3, okay, I. Those are for giants and subgiants. And the giants are what the stars would be. If you have an M3, M Roman numeral 3, well, that's not one of those little dwarfs. That's actually a giant star that is done fusing its hydrogen. And we look at its spectra to determine all that. So we have two ways of classifying stars. Then we have the color OBAFGKM, bright blue to cool red, and we have what's called a luminosity class. We have the spectral class, the color, like I said, and we have luminosity class. Luminosity means how big is the star, effectively. The bigger the star, the more luminous, right? The more energy reaches our telescopes. And that's just what we're seeing here. We're seeing that these stars are really luminous giants, which means that they're probably, class 3, luminosity giants. And so it's always two things. You're gonna, like our sun is a G5, Roman numeral 5. A G5 means dwarf, hydrogen fusing into helium, normal. Now, within the letters, the colors, you also have numbers. So you have G0, G1, G2, G9, all the way to G9. We're a G2, number 2, followed by a V for the Roman numeral 5, indicating dwarf. Yeah, we got thunder out there. So hopefully we won't lose power. If we do, I'm sorry ahead of time. Okay, so that said, you have your little bit of a primer on stars, and so now we can move on to something else. After all, stars are the only reason we see the universe, aren't they? They really are. I mean, without stars, there's nothing to illuminate the universe other than energy that we can't see coming from, say, black holes, or energy that comes from the center of a galaxy that's really what we call a peculiar galaxy that has a strong radio emission. So it's pretty interesting. Let's go here. And now what I want to do is take us to another location here in Canis Major, the Great Dog. Okay, and let's just go a little bit to the left here. And I want to get rid of this. Now this, okay, this is neat. This little guy is what's called a planetary nebula. This is the kind of thing that is left behind after the sun would die. Okay, so we're gonna see that here in just a sec. All right. Okay. All right, let's get it in here. All right, this will stop in just a sec. All right, let's there it is. Okay, this is what's called the was it the albino butterfly? Is that what it was? I don't know if it was albino butterfly. Let me go back and just check. Albino butterfly, yeah. Okay. So the albino butterfly is a interesting object, right? And the reason it's interesting is because of the fact that it's the result of a star like the sun after it dies. Okay? What's left behind is a white dwarf. So after that red giant phase, the star will shrink down, shrink down, shrink down to something about the size of the Earth. And that becomes what's called a white dwarf. Now those are very, very hot. And they're not doing fusion anymore. They're just hot with remnant heat from their original multi-million degree temperatures. All right. So let's take a picture of this. Let's grab a guide star first here, and let's do this first. All right, do this. Hey Sam S, how you doing? Hey Science Bob, what's going on? You're doing M81, M82, excellent. The Bode's Nebula. Yeah, that's great. I'm just reading here while we're looking here. Let me grab, there we see our stars. The system sees the stars. This is just to make it viewable for me. Okay, so we'll do this. Alright, now we're going to go and select the stars. Perfect, that's a great star. Look at that peak. That's a beautiful peak to guide on. That'll render a beautiful result. Now we're going to check this out. And I have us at this unity gain 100. So we're going to try that again with this. And we're going to go 25 seconds here. Alright, so this is now you're going to see, well, you'll see here, you're going to see a beautiful planetary nebula showing up here. Now it's smaller, but our telescope can handle it. Black raspberry soda from Avery's. I don't drink soda. I just wanted something carbonated, so this is nice. All right. Yeah, there it is. Look at that. That's going to be cool when you see that. So we're going to stack this now. And because we have what's called a lot of dynamic range on this, we're going to be able to see this outer extents, they're very, very faint, and the inner extents, we can drop those sliders down to show what's going on inside. This is cool. Yeah, the albino butterfly. And we'll drop this guy out because we don't need it. And look at that. So now what we'll do is let's do this. Let's see where it wants to be. It's going to do that. I know it's going to get brighter. Let's color correct. Get our dark sky and then pull this down. This is a very, very colorful nebula. You can see it's got blue and red in it. It's just stunning. And the reason it's got this in it is because what you're looking at is actually the outer envelope of the star. Because when the red giant, remember I told you when that core collapses, it pushes the outer layers away? That's what it looks like when it does that. But you'll notice it looks kind of square almost. Well, what you're noticing is that the star was spinning. All stars have a rotation rate. Some are fairly slow, some are exceedingly fast, so fast that they warp their shape into like an egg or an oblate spheroid. Well, you look at this, and what you're seeing is a spinning star. Maybe the axis was right here. And so it's spinning, and as it was spinning, it throws all its stuff out equatorially, perhaps. And that's what we're seeing here. And what's it throwing out? What it's throwing out is the stuff it was made of. And most of the stuff, there's a lot of stuff in this nebula, by the way. Not more than we can possibly see here. And when we actually look at the components of this, we'll be able to do this, by the way, when we get our spectrograph running. We'll be able to do a spectrum of this and see exactly what it's made of, right down to each element, which is pretty cool. And but you see the red? Well, that's hydrogen, minimally. It can be a lot of hydrogen because that's hydrogen emission. And then we see a bluish green, and that is oxygen. Now, I talked about oxygen in many times in the past, saying oxygen is the third most abundant element in the universe. And if you ionize it twice, you kick 2 electrons off of the atom, then you get when they come back, you get a green glow. When they come back in to give off that energy in the form of light. Hydrogen does that with its 1 electron and gives off its energy in the form of light that looks red. So we see this looking just like this. Now I'm going to zoom in more here. Okay, I know it doesn't look as good right now, but I'm going to try and drop down the noise level. So you can start to see there's like 2 objects. That's actually it's got a double hot spot in here. So this star has been ejecting material, and then after it ejects all this material, it's going to end up just cooling down. And when it cools down, it's going to end up taking billions of years to cool. All right, but this is just a beautiful nebula that I thought you'd like to see because it's right nearby. Let me do that. Okay. So I'll save it with annotations after setting the target name. All right. And we've got 8 images stacked here. I'll go to 10. All right. So you see, this is star death. This is what star death looks like. You know. When you look at some other objects, what ends up happening is that other objects will actually cause their entire outer envelopes to blow off long before they actually die, long before the star dies. And we're going to check on one of those too. And that's going to fill the screen. It's massive. All right. And you're going to see mostly oxygen in that one. It's going to be teal, greenish, blue. Just a fascinating place. Or let's see now what's going on in the chat. Bob, what are you shooting M81 and M82 with? Are you using like a C-Star or something? I don't know what you got. Alright. And we have XM Vibes. Down from the heights reels the glittering Cassiopeia as the hours wear on. Very nicely said. Very nicely said. And did I miss a question? Did Sam ask something? Oh, what time did we start? Okay, sorry. Yeah. Well, thank you, Lori, for answering that. Yeah, Coma Berenice shimmers weirdly afar off in the mysterious east. That's cute. Hey, you see, you're a poet. I love it. I like that poetry. I also mentioned earlier, I'll say it again. If you guys, those of you that are Patreon subscribers at any level, you get the music album that we created for free. 10 songs, all written and composed by yours truly. Don't be too hard on me. They're actually beautiful. I mean, when I started, one of them I played, one of them called Dreams of Europa. It's it ponders life on Europa, because I think there's potential life under the ices of Europa, and so I did a song about it, and the song was really nice. It's beautiful, and there's another 9 others beyond that, and that's not all there is. I've got a lot more that I've done. I've done music composition and writing for decades, and now I just been putting into practice. I guess why not? Okay, this is gorgeous. This is looking good. I said 10, right? Now it's at 15. I'm gonna save it here. Beautiful. Okay, so this is star death of a star like our sun. Okay, and so now let's go check out what star death for a star not like our sun might look like. Actually, we don't have a supernova remnant to look at right now, but we do have one. Actually, it's just giant. And what I'm going to do now is fit the height here again. Okay. Now what I'll do is take us over here. I'm going to show you another type of process that goes on that's really a crazy process in the universe, and that is this guy here. So we talked about the different types of stars and how hot they are. The O stars are the hottest stars there are, and those stars being that hot, they give off a lot of their energy, so much so that it all just it goes off the star, and we end up losing most of the hydrogen. It's fused into helium so fast that the star runs out. But some stars are oddballs. They're way more, much more prolific and violent. And this is one such star. It's so violent and prolific, and this is just going to be a finder. I think it's right here. There it is. That it's gonna actually be a star that is gonna go supernova someday. But right now, what it's done is it's literally shredding itself. And what you're gonna see is a star that's shredding itself. You'll see the actual star. Basically, you're gonna see the core of the star. That's all we've got to see here. All right. And then you have a nebula around it of all the gas that used to be in the star. Now, if we were in this region, anywhere near this, it would be curtains for us. We would be done. We could never, ever survive any kind of proximity to this type of star. As you'll see, that's a beautiful curve. Look at that. Wow. Okay. So, this is going to be a 35-second photo. And we're going to raise the gain to 200. Okay. All right. So we're on our way. We're taking the picture, and we're going to go right to the live stack because it's in there. I can tell, and it's going to be inside this frame. All right. So now we're going from a star where you saw a red giant in a cluster. You saw what happens after the red giant. You saw that planetary nebula. That's the result of a red giant, shrinking back down, leaving behind just a white dwarf the size of the Earth. And now you're going to go to a very supermassive star that's even hotter than the hottest O stars. These stars are massively hot, and they have such strong stellar winds that they blow off all their outer layers. And they're violent. They can rip you to shreds just with their light if you get anywhere near them. All right, so the star that's doing this in here is not this guy, you might think, right? But it is, and I will show it to you. It's this guy right here. That is the star that's ripping itself apart. Right? This is called Thor's helmet. You'll see many different layers in here. If I bring this up, you'll start to see. And I'll darken up the background to help the contrast. Right? You've got like a layer here that comes out, a layer here that comes out, dark dust here that might have been in the star that's been literally kicked off the star. But I doubt it. I think this might just be in the stellar neighborhood. Then the star is actually blowing bubbles around itself. That's what it's doing. And then because it's in a region where there's material moving through, we don't get a perfectly spherical release in all directions. What's happening is that this star is actually, as it releases stuff, it's encountering other stuff, which slows it down, causes it to glow more than the other side, where it's more free to move out. Okay, so it's getting impeded at this side by denser material, other dust like this perhaps, in the interstellar medium. That's causing it to slow down, heat up, and glow brighter. So everything happens for a reason in the universe, and it all happens that way. Let me drop this guy down, and let's do that to show you this in full size so we can watch it develop before our eyes. Isn't that cool? Thor's helmet. Let's get it lined up. There we go. Save. Oh, I meant to do this first. Set the target name and then save annotation. Yes. All right. Okay, so Thor's helmet now is one of these places where it's a very inhospitable place to be. Okay, you couldn't survive here for a fraction of a second. The hot radiation coming off from this star, besides the temperature being upwards of, the surface temperature on the sun's 10,000 degrees. The surface temperature on this star could be 200,000 degrees. Okay, so we're talking very, very hot stars, and the stellar winds are so powerful that they would literally strip you to nothing, to atoms. All right, and the ultraviolet radiation will just fry you in a split second. Is Marianne here? Oh, we're at radio. There's Ronald. How you doing? Ronald, this is Thor's helmet. Maybe you wrote that earlier. Oh yeah, there's Marianne. Yeah, Marianne is actually out by the observatory tonight in Benson. She'll be visiting it at some point just to check in on it, because, the telescope gets lonely. We have to see it now and then. Yeah, I know, it's a lie. I'm kidding. But she will be there. She is there. Sometimes you'll actually see her on the camera. She'll come in and she'll wave, But, and Marianne has a new addition to her family. And that new addition is... it's almost embarrassing to say. It's a Chiweenie. A Chihuahua and some other dachshund, something or other. It's the cutest thing. And her name is Peanut. And she's affectionately known as Little P. I call her PP, but that has another meaning. But she's really cute. Yeah. Beautiful. So you can start to see. Now, Ronald, you're asking me about the real physical helmet. No, I don't have that on hand. I can't do that, unfortunately. Let's see if we can get... Yeah, we're gonna do that. Now this is interesting because it's showing a lot of the detail. There we go. Okay, so you can see now that it's got these There's some hydrogen in here, which is glowing red. There's dark nebulae or dust all throughout here. So this is an area of the universe that is full of dark dust and material. It's part of effectively one of the galactic arms. So we're seeing a tremendous amount of dust and debris in here. So when a star like this is shedding its outer layers, this entire region is very tumultuous. We don't have a lot of ability to calculate how it's actually going to spread out, because we don't know how dense it is over here versus over here. But by what we're seeing, we can actually build models that tell us what the interstellar medium in this region looks like. But this star is probably also rotating pretty fast. Why? Because you see this long arc here and a long arc here. You can almost see that the star is rotating kind of like this, right? And there's an arc here, and there's also an arc here. So it's almost like it did an expulsion of stuff here, rotated around and went here and here. So it's going and then, you know, it seems like it's doing it in a variety of directions. Really neat. And then what do we have here? Oh yeah, Karen. Karen Belmont's gonna head out. Okay, good night. Thanks for coming, Karen. See ya. Bye bye. Bye bye. Karen manages logistics for a trucking company, if I recall, and so she's got to be up early and all that. Happy horsey poopy. Okay, let's take this and just drop it down just a little. Darken it up, and let's color correct one more time. There we go. Look at that. So this whole area is also bathed in a gentle glow of hydrogen, which is sort of red, and you can kind of see that. Really neat. But again, exceedingly dangerous to be anywhere near. So now you're going to ask me, well, though, how far away is it? And let's actually go look and see if we can get that distance. I doesn't have a distance here, and this is the kind of thing that I would ask Daryl to just grab while we're talking. But Daryl, I didn't ask him to join tonight. He will. I'll have him back soon. You know, he's been kind of under the weather. Not sure how he's doing tonight, but he's sort of touch and go on some things. So when he contacts me next, I'm going to ask him if he's ready to come back on the air and hang out with all of us. He really likes doing that. He's really good. So look at that. You can see some detail in there. Now, with the wide field scope, the entire Thor's helmet is about this big. But with this scope, we're capturing detail we just cannot see with that other telescope, because we can actually zoom in on this even more, you know, and see details. Look at that. That's really cool. Now, remember I was talking about stars the size of Jupiter, like red dwarfs? This guy is probably a red giant. It's very luminous, so I could make that kind of assumption. It's probably one of those. But then if you look elsewhere in this view, you might find some really small red stars, okay? Like that star. That star is really red, but it's small, right? This star is red, but it's small. Nowhere near the brightness of this. So this may be one of those M dwarfs, you know, the Roman numeral 5 kind, which is a little bit bigger than Jupiter, about the same size. And that's what these might be. This is definitely a star. This one up here is definitely a star that is larger in diameter, because it's showing quite a brightness. And the closest star to us that is a dwarf, like that, is about 6 light years away, and it's not even remotely this bright. It's actually dimmer than this, you know. If I recall, it's more like this, and that's an M dwarf, Barnard star, actually. So pretty cool. A lot of detail in this. Holy cow, that's really pretty. Let's see if we can tease out some more detail with our enhancements. Let's do this. Okay, so that added some more detail. You can see this stuff here. This, again, remember I've talked about this dark nebula. If you're a star forming region, forming a star inside this dark nebula, you might be protected and survive that. However, I don't think that you'd survive this one, because this star's radiation is going out many light years, okay? And it would probably sterilize anything within this nebula. It'd probably reach within this dark cloud, yeah. Benjamin Major, how you doing? Oh, Benjamin, yeah, no, that's actually a star that's in the field where this object is, okay? Let's see if we can tell you what that star is. Let me see if we can find it. Probably not, because it's really buried inside this field of view. It's going to be, let's do this first. It's going to be this guy right here. All right. And I don't, hey, look at that. It does. It tells us, yeah, it doesn't tell us the spectral type. It's just, it's a star. That's all we get to know. That's all you get to know, man. And that's it. I don't know. And the other bright star was this one next to it. Our screen, by the way, just so you see, if you look at this, it's upside down. Okay, the telescope's looking at it kind of upside down, so it kind of looks like that. Right. So we got to flip this right side up to kind of get. You got to look on your head to see what you're looking at. So top right, we have these two bright stars. Okay, top right, we have these two bright stars. Okay. That's really pretty, though. This is one of the best views of it we've done. Really, really nice. Wow. I'm very happy with how this is coming out. Hopefully you are too. Alright, so let's save this with 22 images. Now when we get the spectroscopy going, we'll be able to basically take a line through this and analyze the data and tell exactly what we're looking at. I know we're looking at oxygen, but we're going to see other elements as well in there. And that's really interesting to see what things are made of. You know? Benjamin says, red means it's an old star and the ends of its life. In the case of a massive star, yes, Benjamin, that's true. Betelgeuse, for instance, Antares, for instance, VY Scuti, for instance. However, not for a star, okay, like Barnard's star. As I'll tell you this, the color is not what determines the star's life. It's its size and its mass. And its mass is more associated with a characteristic of stellar classification that we call luminosity class. So a star like this can be a M-type star, which is a star that's not very hot, but that can be because it's very, very large and its outer extents are very, very cool now because they're so far from the fusion going on in the core. But those outer extents, why is it out that far? It's out that far because it expanded that large because it ran out of hydrogen and it's fusing other things now. Helium into carbon, carbon into oxygen, oxygen into other elements, all the way out to possibly iron if it's a very massive star. Okay, so we classify those with what we call luminosity class. So a star that's a supergiant red star is the same temperature as, say, Barnard's star, this tiny little red star, and looks the same in the view, kind of. But Barnard's star is going to be a star that has a V after its name, so it's a regular dwarf fusing hydrogen into helium. And then a star like this is probably going to have a different designation after its name, like a Roman numeral 1 with a little a. And that means a supergiant. Or a Roman numeral 3, III, right? Like a giant star, or 2, a Roman numeral 2, II. And that means that it's done fusing hydrogen, and it's in that stage of its life where it's going toward the end, yes. So you're half right on that, okay? But I will say this, the bulk of the stars in the universe that are the little red ones that we're talking about, that's the largest population of stars in the universe. And get this, the universe has been around for 13.8 billion years. And the very first M star that was formed is still going strong. And it will for up to 1 trillion or more years. They are really long-term stars. They last a long, long time. They're the longest lived star in the universe, right? So those little tiny red stars have the longest life, but the big giant red stars are among the ones that have the shortest lives. Confusing, right? It just has to do with how massive they are. The little red ones are maybe 1/10 to 100th the size of our sun, and the massive ones are 50, 30, 100 times the mass of our sun. And they've expanded outward as they stop fusing elements. So this is kind of cool. So yeah, and that's true of all stars. Okay, in a way. You can have an O. See, O stars tend to be massive anyway because they're the hottest and bluest, and they only live a few million years. The farther on down that table you go, from the hot blue stars to the white stars to the yellow stars, okay, to the orange stars to the red stars, the farther you go down that list, which is called the Hertzsprung-Russell diagram, the longer lived the stars tend to be, as long as they're doing just hydrogen into helium, okay, and that's called the main sequence. It's a snaky line that you see when you plot them. When they're doing normal hydrogen fusion, if you plot them on a diagram, they all have they follow a snaky line. But the ones that are not on that main sequence, that are out above or below, those are stars that have stopped fusing hydrogen into helium, all right, and might be fusing other elements into other elements, okay. So, and those are the ones at the end of their life, but those are usually more massive. Okay, how many did we get here? We've got 31 images here. This is great. So let's redock this, and we get our. Look at that, guys! Isn't that beautiful? This is live. This is live. We're seeing this right now live. Now, as far as this object, I want to share something here. I gotta figure this out. I want to do something here. All right. Let me do this. I'm doing something you can't see, so momentary. Hold on. Whoa, that's wrong. I couldn't type. I'm gonna just grab the distance to this. I think I know it, but I'm not gonna speak out of turn. I should have spoken out of turn. It's around 14,000 light years away from us, so you're seeing it as it was 14,000 years ago. Now, what's neat is, for those of you that have been with us, you know now that I like to put what we're seeing in terms of what was happening on Earth, a long time ago. The time the light left there, what was happening here on Earth. Now, in this particular case, 14,000 years ago, we were undergoing a big thaw. We were actually coming out of an ice age. And so we ended up finding that our climate was a lot colder than it is now. Okay, so in a sense, when you hear people talk about global warming and all that stuff, you have to understand that they're not seeing the whole picture. The Earth has been warming for tens of thousands of years, and it's long before we got involved, you know. So something's going on for sure, and yes, we can certainly make a difference, and we can affect it. Yes, not going to deny that. However, we also have to understand that we're not the only factor, and the Earth and the Sun have their own time frames. You know, they have their own time frames. Okay, 35. I'll save it here. So when the light you were seeing tonight left here, we were coming out of an ice age, and it was much colder in the world than it is now. Okay, we had glacial lakes, and this light has been traveling to us all that time. We actually saw something where the light traveling to us was left before the sun was formed. 4.6 billion years ago. Unbelievable. Okay, let's go to the next object here. First things first, we've saved it. Now we'll go to our low light mode and then do the over processing to show us the image. Okay. All right, so we've seen red giants. We've seen planetary nebulae, the ultimate demise of red giants, kind of like our sun, and then the planetary nebula. We've seen these specialty stars here, like these stars actually have a special name. They're called Wolf, like the animal Wolf Rayet. Wolf and Rayet were two astrophysics guys who discovered these particular stars, and they were very, very powerfully active, and they had a tremendous amount of stellar winds that blew their outer layers off, like we talked. So really neat. Now let's do one other before we go up to that. While we're here, there we go. I want you to see this one, or is it this one? This one. Okay. Now, here's another one that we're going to go to, which is really interesting. Okay. Now, this is a cluster of stars. Okay. And in this cluster of stars, we're going to see another planetary nebulae. Rather than another satellite that went zipping through. Okay. It'll stop in just a second. We're gonna have it. There it goes. Okay. So I'm gonna bring that back now. Okay. This is what's a fascinating stellar death. Okay. Because here we have a cluster, and in this cluster, we have what appears to be a planetary nebula. But wait, aren't planetary nebulae supposed to be... aren't star clusters supposed to be young hot stars? Yes, they are. And this particular cluster is full of hot young stars. So why do we have a dying star in a cluster like this? Now that's odd, isn't it? And these are the kinds of things that we think about. Well, I am going to show you how this happens. Let me just take a photograph of it. First of all, let's grab our guide star. Okay, this is really interesting. This is a cluster, and the cluster is known... Actually, I don't have to do that. I can just do it this way. I'll tell you in a sec. Let me grab the star. There we go. Another beautiful star to guide on. Okay. So let's grab this guy right here and say we're looking at a planetary nebula, but we're in a cluster known as Messier 46. And we have a planetary nebula in a cluster like this. This doesn't make any sense. Okay? It doesn't make sense. And the reason is because young hot clusters should not see a planetary nebula in them for at least millions of years, depending on the size of the stars, or even billions of years, like with our sun. So what happens here? Well, I'll take a photo, you'll see it, and we'll be able to talk about that. All right, so this this particular object we're guiding now, so I'm going to just take a, I don't need to more than 15 seconds actually. This is bright enough. And you'll see the cluster and you'll see this object. Now the object you're looking at in the middle of this right there, that's a white dwarf. That's the size of the Earth. Okay, now let's come back to this. All right, and there you see it coming in, and we'll get that fixed in just a minute. And okay. All right, so if we get rid of this and do our live stack now, it's been building up on the image sensor all this time, so we're going to see it get dumped out right now. There we go. So here is Messier 46, and here is this planetary nebula. Now, again, the star in the middle is the one that is doing that. Let me drop this out of the way so we can actually check it out. I'm just going to do this. I'm going to do that. Pull this over, pull our black level up to the peak again, just before, and then drag this down to soften noise and allow us to see this object in more clarity. So this object then is definitely a planetary nebula, and this object here, you can't really tell that well, but it's actually a little bit bluer than the other stars. That's a white dwarf, and what's happened is this star has given off a shell of material on all sides. And so to show you how this works, okay, and this is the mystery, when you look at this shell of material around the star like this, every place you see this star from, no matter where you are in the universe and look at it, it's going to look like a donut, like this. We're not looking at a ring with a hole in the middle. We're looking at a sphere. Now watch my hands down here. When you're looking at it from the front and back, you can see through my fingers. You can see my face through my fingers. But when you go around the side, you're looking through more material. And now my face is not visible because you're looking through more material. So here you see very little material. Here you see more. Here you see very little material. Here you see more. So this is the illusion that a sphere creates when it has a tenuous envelope around it. You have the center looking like this. When you look face on, you're looking through less material. When you look at it from the edges, you actually see it through a thicker amount of material, and that's what we're looking at. So this object is fascinating for that reason. Now, here's the interesting thing. This cluster is, I think, 1,500 light years away from us. Let me go here again. Messier 47. It looks like, I think that's 1,500. Let me, yes, 1,598 light years, okay? Now, that said, oh, that's Messier 47. My mistake, I'm in the wrong cluster. Okay, I thought something wasn't right. We're in Messier 46, right here. Okay, so let's grab Messier 46. You got to see this. I got to tell you what's going on here. Messier 46. Okay. All right, so Messier 46 then, that we're in, this cluster, its distance is actually 5,545 light years away. All right. Now, is this object also that distance? That's the question. Now remember, this is a projection of the universe that we're seeing, right? It's a three-dimensional universe. So these stars, some are closer, some are farther away. What about this? Well, if we actually look at that object and just that object, okay, this guy right here, well, this one isn't 5,500 light years away. Its distance is actually 3,900 light years away. It's actually much closer to us. So this is a foreground object. It's up here, and the cluster's back here, and we're seeing it as if it's in front of it. Isn't that weird? So this is one of the things we have to figure out sometimes. And Benjamin says, Bubble Nebula? No, this is a planetary. The bubble's actually very red. And the bubble is the same kind of, made by the same kind of star that Thor's helmet's made from. It's a Wolf-Rayet star. Very, very highly volatile star, blowing off its outer layers into the outside. And let's see, we got Double G videos. Just shot M46 back on the 8th for the first time. Was surprised when I saw that after processing. Yeah, you found this amazing planetary nebula sitting in the middle of it. Notice it has a little red ring around it. That's a hydrogen layer that was sloughed off of the star. When the stars like these, like the sun, get older, then what they do is they will swell into red giants, and then they'll shrink a little bit, and they'll swell, and they do what's called a thermal pulse. And by doing this thermal pulsing, they'll push off their outer layers, puff, puff, puff. And sometimes the layers are hydrogen, sometimes they're oxygen, sometimes they're both, like here. You see the hydrogens on the outside ring here, then you got oxygen in the middle here. Okay, it's pretty cool, you know. And Benjamin, you're not, there's no ignorance here, trust me. I asked questions like you did years and years ago before I became an astronomer, so I don't have any problem answering them. If you don't know what it is, you don't know what it is. So you're allowed to ask, and we welcome the questions. So that's very cool. Let's see. Uberku says, I have a question about the software that would take away from the moment. Or could I reach out over Twitter? Oh, you can ask now, or you can actually reach out by going here. Write me a message, Uberku. There, contact skytour@gmail.com. Not a problem. I always have the email on the screen here, so you can do that. Join us in there, you know. But if you have a question about the software, feel free to ask here if you want. Not a big deal. All right, let's do this. Let's fit the height again. But that's a beautiful one. I wanted to just show that to you. I didn't say anything. Hey, Wayne Pinkham. Wayne's with us. Wish Wayne a happy belated birthday. I think it was yesterday, he told me. I thought I got it right, Wayne. I'm sorry. I thought it was on the same day. Wayne's cool. He went to Mauna Kea out in Hawaii. Brought me back the coolest shirt. I always talk about it, Wayne. I'm sorry. And it has, you know, all the mirrors for all the telescopes on the mountain on it. And it's for the observatories up there. I really love it. It's a great shirt. Just wore it the other day. Yeah, fantastic stuff. Okay, so now I'm going to redock this for now. There we go. How beautiful. Let's see if we can pull that in a little bit. Yeah, there we go. A day late is okay. Okay, thanks. Hey, Desert Dweller, what's going on? Desert Dweller says hi to the Sky Tour crew. All right, man. Thanks, brother. Yay, brother. Okay, there we go. That's beautiful. Now I'll save that. Oh, I should wait because I got 30. I'll just save it again. And then we'll save exactly what you see. Here we are. Okay, so you'll have this guy too. And I think I did this, but I'm going to do it anyway. Maybe I didn't. Let's do the annotated image and then save the image with annotations. So now you can see what it is and see its information if you're interested. Okay, thanks, Ubercool. I'll talk to you whenever you want. Okay, and now we're going to come out of here. Let's go back to this. Low light mode. And even in low light mode, we get a hint of this ghostly image there. And that's pretty interesting. So that is star death like the sun. Again, kind of like albino butterfly was. Okay. It's just different, and it looks more like the Ring Nebula, right? But now, I want to show you an area that has a fascinating. I'm going to see if we can go there too. there is a fascinating... Yeah, here we go. This is a nice stellar nursery. That's really cool to see. We're gonna go here as well. You haven't seen this one for a while, if at all. So let's go down here. We're coming right in. We're careening in. There it is, right there. We're careening in at high speed. All right. Okay. So I'm gonna bring this down into the view. It's coming into the view, but I'm gonna actually bring it further down into the view. Okay. We're going to look at the center of this nebula because it's bigger than the field of view, which is the case for this telescope. This telescope is great at looking at details, which I really love. Okay. Let's do that. And then this. Pull it back a little bit. Pulley backy, pulley backy. Okay, that looks like it should work. One more jog. There we go. Okay, so now we're going to be looking at this guy. Okay. And you'll see that it's bigger than our field of view here, but we're gonna be just fine. So it's right there. Okay, very nice. And we'll synchronize to that spot. Okay, so now this is the Skull and Crossbones Nebula. This is an area where stars are forming. So we see star death. Now we're going to see stellar birth and the place where stars are forming. And this one's going to be a 55-second shot. Okay, we're going to grab a guide star and do that. So there's our new field. Let's grab a star. Where's the star? Okay, there it is. That should work. That should stabilize into an... Oh yeah, look at that. Beautiful curve. That should be a good curve. Okay. So now we're starting a 55-second shot right here, which will jump right into the stack. So when we talk about stellar birth, you know, how do stars really form? Well, they form from the most plentiful element that the universe has. That's hydrogen. So if you get enough hydrogen together, hydrogen atoms have mass, a tiny amount each, but when you have a bunch of them out in the middle of space, they will attract to each other because there's no other mass around, perhaps. So they start to combine. They build up and build up and build up. The bigger it gets, the faster they accrete more hydrogen atoms and hydrogen gas, along with other stuff. And so in that center of that growing cloud, the overlying pressure is pushing down the gravitational pressure, and that pressure translates to heat. Okay, look at that beautiful nebula. All right, and that pressure translating to heat is what's eventually going to light up a star. And so when you get enough heat and pressure in that central area, then you reach a certain threshold. It's called a nuclear fusion threshold. 15 million Celsius. Pretty hot. But what that does for you is it makes you go from being a cloud of hydrogen gas to being a star, where hydrogen fusion is occurring now because the overlying pressure is so great and the temperature is so high that you can now take those compressed hydrogen atoms in the middle and crush them together to make helium atoms. That is the basis of nuclear fusion, and that's what we're seeing going on in stars. Now let's do this. Look at that beautiful nebula. So this guy here, this is a lot of hydrogen gas out here, but it's all diffuse hydrogen. It's not coalescing and making dense clouds of hydrogen. a dense cloud of hydrogen will occur if you see like this red area. The redder it is, the denser it is. Okay, this is a soft amount. The amount of hydrogen in this area might be only a few atoms in the size of a sugar cube. Okay, in this area here, it's a little denser. Maybe you have 30 atoms in the size of a sugar cube. For comparison, air has like 10 to the 19th or more atoms in the size of a sugar cube area. So it's actually a pretty what we call a medium that's not very dense at that point. Okay, and that's rarefied is the word, but but that's okay, because over the size of that compression occurring in these nebulae, those areas can get denser and denser and denser locally, and when they get to that threshold I talked about, then you get a star, and then that's oversimplification, right? I mean, I think I mentioned this when we did the when I was getting my degree in astronomy. One of the things I had to do was to build a star on the computer, and using only the book Stellar Atmospheres by Ivan Novotny. Stellar Atmospheres is probably the most difficult book you'd ever read, because it talks about processes that happen in the star at different levels, and we had to recreate those computationally on the computer. My star worked. I had a star that worked. It was great. And I had to show it all the different layers what the star was doing, and based on the structure, it did all the right things, which was nice. That's good. I can build a star. However, again, we're doing reverse engineering, right? We're doing reverse engineering of the universe. So that said, hang on, I'm just changing temperatures here. So there it is. So the skull and crossbones. Now you might say, I don't see a skull, I don't see crossbones. Okay, well, this is where imagination comes in. Okay. Imagination is very important here. Now going back to our stellar types we talked about, this little tiny red star right there you're seeing, that's probably an M star. That little red star right there, almost certainly a little M star. That little guy right there, an M star. When I say M star, I mean the dwarf, the little tiny guys. The guys that once born will not die for trillions of years, perhaps. Like I said, the first M star ever created in the universe is still working just fine. It's not even through the midway in its life. Amazing it can live that long. Okay. So we've got a 55-second exposure here, and we're using a gain of 200. So we have, some grain, but not a lot. We can still make it grainy just by doing this. All right. And that's actually not so bad. But you see what's hidden in the back right now. But that's cool. So we have oxygen in here in this region of the nebula as well. And then we have all this dark dust in here. Look at all that dark knots of dust. And you'll see interesting location right here, guys. If you look, you see this dark area, but then you see it looks a little bit reddish, but it's still dark. What's going on there? This is an area where you have hydrogen and dust that are mixed together, and you're getting the ionization of the hydrogen from this hot star cluster in this region. Okay, and whenever we see a nebula like this, there's a cluster that's causing it to glow, and in our case it's going to be this hot young cluster right here causing all this to glow, right? And the glow can go out for light years. It's amazing. All right, so this beautiful cluster is probably responsible for illuminating most of this. There might be other stars in here that are helping out. I'm not sure about this star, if it's in the cluster or it's a foreground object or a background object beyond this star cluster. I'm sorry, beyond the nebula. But look at that interesting illumination on there. And you have dark material here. Now, there's undoubtedly hydrogen mixed into this, but not enough to show up. And so the dark dust dominates. Now, I keep saying dust, dark dust, dust. What is the dark dust? Okay. Remember the red giants we were talking about? The bright red, big red giants? Okay. They're so large that the outer fringes are far from the fusion going on in the center. So molecules out there can form. Sometimes we get molecules forming, compounds forming out there. And they can be things like carbon atoms that are combined. And then they combine with other carbon atoms, making a molecule of sorts, of all carbon. And that makes a tiny, tiny little dust particle. And those tiny, tiny dust particles are fantastic, Hey, Wayne, thank you. That's so kind. But Doneo, you got me that shirt, man, and that cool Oumuamua postcard. Thank you, brother. That's really kind. Thanks, man. But yeah, so if you look then at if you look here, when you look at, did I miss something else too? I think I missed somebody else. Did you do that twice, Wayne? Or is it just one? I think I see two up here. I don't know if you did one or two. Well, look, one is wonderful. Thank you so much. This is awesome. Thanks, brother. So when we look at this dark dust, then it can be carbon molecules, carbon molecules. It can also be silicon, because silicon. Now here's a weird thing for you, okay? Silicon is formed in a star, right? A very, very heavy, massive star. And silicon, which we make all our silicon chips with and all that. Do you know how long silicon is made in a star before it goes supernova? And every star that makes silicon will go supernova. Okay? The actual timeline, the time that a star will make silicon is 1 day of its entire multi-million year life. 1 day it makes silicon. Yet we have enough silicon here on Earth to never run out. Isn't that amazing? That means that a lot of stars have done this. A lot of stars. Really, really amazing to me. So a lot of stars have gone supernova to create the silicon that's in the universe that just happens to be in our solar nebula when the Earth formed, right? Outrageous. Outstanding. Outstanding. So this nebula here, let's check it out. Its distance is about 3,262 light years away. And so again, you say, well, tell me about the Earth. What was going on Earth? Back then. And the answer for that is that you can find, for instance, that was the year 1237 BC. And in 1237 BC, we had giant forests that had, oak and chestnut and beech trees. We had the trees much like the modern day. Okay. But the indigenous people were also very, very dominant in this region where Connecticut is and other locations in the world. But it's remarkably similar to the climate of the 1800s, from the summer to the snowy day. So the climate was actually pretty much the same as today. Now, other thing that happened was that rivers were carving their way, and carving, canyons and things like that, or continuing to carve canyons. So there's a lot a lot that was going on, but that was back then. That was the late Bronze Age, in 1237 BC. Okay, that's when this was. Okay, massive empires. In fact, back then, when the light that you're seeing tonight left this object, the first global trade was occurring on our planet. How about that? Isn't that crazy? And Ramesses the Great, in fact, in Egypt, was the ruler. And he was at the height of his reign when the light you see tonight left this object and to reach our eyes. The time in Greece, it was the time of the Trojan War. And that's the Mycenaean Greece. So, again, incredible stuff, you know. So there's a lot of things going on, you know. The Shang Dynasty in China had just begun. And the Olmecs in Mexico, the Olmec civilizations were rising and coming up. Again, all when the light we see tonight left this object. And it terminates here at our eyes, but it carries with it a whole entire history, early history of the Earth, doesn't it? Effectively. So I think that's kind of cool. And I've been fascinating, you know, I'm fascinated by this, you know. All right, so we are, Benjamin says, we're seeing ghosts in the sky. You know what? That's actually kind of cool. By looking at the sky, we're actually seeing things that were, you know, we're looking back in our own history. If you could go back to this nebula right now and look at the Earth, it'll be 1327 or 1237 BC. Isn't that incredible? Yeah. That's what they'd see if they could look at the Earth with a powerful telescope somehow. Very, very nice. Okay, so Donald Kunzer says, can a star make glass then? Or is it just powder? Well, okay, that's a very good question. Here's the problem. Glass is a substance that's made with heat, but if you heat up atoms too much, then their electrons leave the atom, and an atom needs its electrons to be a solid or so. And so you can't make glass if it doesn't have the silicon electrons in it, okay, because that lattice is very, very important. So when you have temperatures in a star that are so hot that you end up ionizing, say, silicon atoms, then you just have free silicon, all the protons in a silicon atom running around free. Okay, the free nucleus of a silicon atom running around with all its protons. Okay, now, interestingly enough, we did find an exoplanet that was so close to its star that the silicon in the atmosphere was making glass, and so you actually get glass rain. How about that? What an absolutely horrific place to be. You might be alive for a fraction of a split second, all right, to feel one of those shards going right through you, but it'd be like, ah! And then you're just obliterated. Yeah, so that's pretty cool. So planets can make glass in their atmospheres under certain conditions, especially in the extremely inhospitable locations we've seen in the universe. Okay, this is cool. So we saw star death a couple different ways coming. We saw the Wolf-Rayet stars that are going to lead to supernovae. We saw the planetary nebulae. We're seeing the stellar nursery here. And again, this is the Skull and Crossbones Nebula, and I'm going to highlight that. And it's called NGC 2467. But its name is actually colloquially known as, I'll put it in here, Skull and Crossbones. Okay. And then we'll save the image of the annotation. Okay. And that's saved now. Yep. And then we can take the last image 18. That's cool. And remember, you can see all these images at skytourlive.org. You can scroll down and say, I want cool pictures, and just click on the link, and it takes you to our folders that are being made right now. This image I just took is probably already up there, and you can go look at it right now and download it and enjoy it. So if you want highly processed images, or you want to get our musical album, you can just join the Patreon at any level and do that, and we would be more than welcome. I will provide all the Patreon members with links to the album online, and you can download them and enjoy them. Okay, let's see here. I guess I'm gonna wait till 20 here, and then just do an even 20 at 55 seconds. Why not, right? Meanwhile, while we're waiting, I'll go see what else we can look at. There's plenty to look at. We're looking pretty low in the south. We're only 30 degrees above the horizon. But there are some things way down here that are fun to look for. I'm going to do this. DSOs and this and this. Okay. All right. Yeah, see, we're getting into the murk. Not the merch, the murk. Okay, there's 20. Save. Okay. All right. So this is really cool. So that'll be up there for you to check out. By the way, I don't know if any of you follow the Y Files. AJ Gentile. Well, he contacted me a few weeks ago, and they're bringing me to Las Vegas to do a show about SkyTour Livestream for a new podcast he has. I don't even know if it's new, called The Basement. And they just had James Fox on there, who's a UFO filmmaker, good friend of mine, last time. And so I'm going to be the next guest. So that'll be kind of cool. We get to talk about all the stuff we're doing. You know, I mean, this is what I want to do for life, right? I mean, astronomy, that's me. I'm an astronomer. It's built in. But I also study alien life and the possibilities. And boy, oh boy, the possibilities are stronger and stronger all the time. A lot going on, man. All right, let's see what we've got up here. I want to look at this guy here. I was gonna go before. This is called the Seagull Nebula, and I want to go right there because that's the part of the nebula that actually has a very interesting dark lane in it that I want you to see. Theoretically, we are there. Maybe so. Maybe it works. Ben says, NGC 6826, blinking nebula according to Stellarium, is just being nosy. Okay. All right, let's check it out. Let's see where that is. Let's we won't do it right this second, but what I'll do is I will go there. Let's do this. Center this up. And let me take just a quick 10-second shot. Actually, we probably have enough stars to figure this out. Yeah, there we go. Seagull Nebula's right there. But I don't know where they put that cross. That might be. Yeah, I think I see the dark thing. Okay, let's give it a shot. Let's move it over. Let's move it down. Well, yeah, that star belongs there. That's a bright star that's in the middle of it, I think. That should be good. Let's make sure. Yeah, and then that Hipparchus star will line up now once I do this. Okay. Think we're good. Well, we're going to find out. Okay, we're going to do a 200 gain. That's the sensitivity of our sensor. We balance the sensitivity with the exposure time to get the least amount of noise in our image. Okay, so let's do this. Let's I'm also going to be on Night Dreams Radio tomorrow night. And I've been doing that show for a few years. Very nice people. So if you know Night Dreams Radio, you can join us on there. My show is 8 to 10 on Sunday nights on the Unexplained Network. I left KGRA because KGRA, I don't know what happened. They just stopped paying attention to what was going on, I think. In any case, Unexplained Network has made me an offer, and I've taken it. So now I actually will be able to do my 2-hour astronomy show on that network, and that's available everywhere. It's on Roku as well, which is cool. Oh, thanks, Ben. Ben says anything you look at is awesome. All right. Okay, so now what I'm gonna do is let's get this going. Let's do a 45-second photo here. All right, and first things first, let's grab a guide star. Here we go. Grab the guide. Beautiful, narrow and tall. I like that. Okay, that's gonna be a really good star. Okay, we are underway. Underway, 45 seconds. Let's go into deep sky mode here. Hope you guys are having fun. This is kind of cool, isn't it? Almost toxic. I'm almost toxic. Unexplainednetwork.com. I guess that's it, huh? I don't know. It is the Unexplained Network Good Vibes. Previously known as UNX, and they've changed the name to Unexplained. Right, here comes the first image. We should see the dark lane right in the middle. Oh, there it is. Look at that. That's beautiful. Okay. So again, I'm showing you this one. This is another stellar nursery, but I want you to see this one for a different reason. This one actually shows us a couple things in this one little shot, and I'll wait until it gets a little better to start talking about them. But the basis is going to be density of the hydrogen, some of the oxygen, and what the dark nebula in here means to us, which is really interesting. Mike, go ahead, Rick. I didn't say hi to you. I'm sorry. Yeah, blowtorch. Okay. Mike says, anything lately about news lasers or atomic clocks? No. Oh, anything, okay, about new lasers or atomic clocks. Okay, yes. I have, actually, now that you mention that. You know, when a star does fusion, it requires high temperatures and high pressure. But there's another way to do fusion, and that is using high-powered lasers aiming at a particular fuel pellet and causing fusion to occur, and keeping those lasers charged and doing it over and over. It's like using, you know what a capacitor is? It's an electronic component that stores electricity. All right, it looks like a battery. It may have the positive and negative terminals in the top. You touch both of them, if it's charged up, it's like a battery, and boom, you get a shock. But unlike a battery, when it hits you with that charge, it's exhausted and you got to recharge it. Okay, so they're using capacitors now in large systems, many hundreds and thousands of these capacitors all charged up, and they're cycling through them and doing fusion, all right? And that looks exceedingly promising. So maybe that's the way that we're going to end up doing fusion. So I've heard about that. So those they're not new lasers. It's just that it's a new process with lasers. So I guess that's, the idea. XM Vibes says, "Only when my round is over shall the past disturb thy door." That's nice. That's cool. Yeah, so it looks like that's a very promising fusion technology coming our way. Okay, so let's color correct this. All right, you can see the oxygen and this actually might be a reflection nebula. I gotta look and see. Reflection nebula is different from the emitting oxygen nebula, the emission nebula. That's oxygen. The reflection nebula is just the dust reflecting starlight back to your eyes, effectively. And the starlight is going to be hot and blue, especially in a stellar nursery, because that starlight that is the favorite of the dust particle is the blue part of the spectrum. So every star has blue light in its spectrum, right? It's just the varying amounts. Okay, a yellow star has less than a hot blue O star. And the yellow star has more than the red giant. Okay, but you still have the spectrum. Okay. This is showing up beautifully. This is so nice. Let's do this. Let's drop this guy down. There we go. Look at that. Yeah, this is a reflection nebula. Wow. That's just so pretty. It's like a composition. It's like you're doing a painting. We're doing a celestial painting. Yes, that's true, Michael. They can use that technology. Okay, so one of the things I wanted to show you is if you look at this object, you'll see that you can kind of see through the dust in a few places, but then this spot is here. Look how dense that is. You can't see through that. So I'll give you an example. Okay, I mentioned before about the density of the atoms in these areas. The density of the hydrogen in this area is higher than the density of the hydrogen over here. Okay, because it's brighter red, more atoms per sugar cube size that are emitting light. Okay, but then when we look at the dark nebulae here, this dark dust, look how dense this is. Notice it has like a choke point right there. What's going on right there? What's going on right there is likely that there is some gravitational collapse going on in here. And that gravitational collapse could lead, in some years to come, to another star being right here in this spot. You know? That star could be right there. You also notice that the center is dark and the edges are light. You're actually seeing the shading, okay, the three-dimensional shading effectively of this area illuminated by starlight from around there. The starlight is just reflecting off some of these elements here of the dust. And in this region here up above, okay, we're seeing a reflection nebula, right? And this reflection nebula is the small dust that's actually reflecting off that, reflecting back to your eyes, just the blue portion of the light from the star that's in there, or the stars, plural. So that's cool. Now, one way to see more detail is doing this. You can actually reduce the size and capture more detail with your eye, and then you can zoom in and say, well, let's take a look at just this section right here. You know, so then you can zoom in here and see that. But that's kind of neat. I'm going to color correct one more time. See, once you get to the point where the color is fully corrected, you don't have to do that anymore. Now I'm going to do this, and it's going to drop it down on me. So what happens is these values, this is the data, the white curve that you see in there, that's the bulk of the data. This is the black level. If I move it here, we move it off, and we get this fuzzy look. This is not looking at the natural sky. The sky is very dark, but we're inducing additional light in there, or a lightness that we don't need. It's like changing the contrast. So if we ride up the curve just before it reaches the peak, that's the darkest that we can make it. And this is the mid-level. This has all the other light values in it besides black. And as we move this toward the curve, you'll see that we've increased our noise a little bit, right? But we're seeing more detail. So the way we do this is we play off of this one and this one to try and get the best blend. So this one I'll back down a little bit, okay? And this one I can just take down a tiny bit, right? And now what this does for us is it allows us to see the detail without seeing a ton of noise. And this is really, really cool. Okay, so I've taken 12 shots. I'm going to save it. Save exactly as seen. All right. Lori LDP, thank you for coming. You know, I have to start later because it gets dark later out in the West Coast. I'm in Connecticut. So it's after midnight for me, you know. But thank you for coming. I'm not going to be around much longer myself. Benjamin says like diamonds in velvet. Yeah, that's a very, very good way to put it. Thanks, man. All right, Lori, have a good evening. So anyway, when we look at this stuff, you know, every single image that we take, they all have different appeals, different meanings, different origins, and they also show us different things about the universe. And that's kind of what I'd like to share with you. You know, it's all these different things. Oh, Marianne's still here. That's cool. She's down in Benson. I wanted to mention to you guys that if if anyone wants to give us a donation of $25 or more, for a $25 donation, you will get one of our Sky Tour live stream T-shirts. It says Sky Tour Live on the front, on the back. It actually has the planets, all 9 planets, including Pluto, because I believe Pluto is a planet. And it says in the middle of it, it has a ring of the planets, and it says, I need my space. It's a beautiful T-shirt. They come in black, and we have a number of different sizes. So if you want a T-shirt, let me know. Just $25 donation or more will get it to you. You can donate via the Super Chat. We take Zelle to contactskytour@gmail.com is the email. And so you can do it that way. We're currently trying to get our donation system back up and running on our skytourlive.org. The company is the company that's managing our nonprofit website is they declared Chapter 11. They're going bankrupt. Okay, that is called Flip Cause. Don't use Flip Cause. Okay, so it's a risky investment. We didn't know. Well, we never. I always do the wrong thing. You know what I mean? What can I say? I just. So anyway, we're trying to get that back up and running privately outside of them. So Zelle or a Super Chat will work fine. And you get for every $25 donation, you get one shirt for $25, 2 shirts for $50. And beyond that, we'll talk. All right. Anyway, I hope you guys are enjoying tonight. So this is looking pretty. I'm gonna redock this and get us back to fitting the height. Oh yeah, Ben. They were looking when they were showing Pluto. Yeah, I was I was watching that live too, and the first images came in from Pluto, and it was the coolest thing watching that. And we saw the heart-shaped, like was it Sputnik Planitia, showing up. We saw Pluto's atmosphere, which was mostly oxygen. Holy cow, Wayne! Are you sure? Well, you're getting a T-shirt. You want two? Let me know, Wayne. That's a 2 T-shirt donation, brother. You live right down the street from me, so you can just... actually, Marianne's going to have to send them to you from Arizona, but... contact me at contactskytour@gmail.com, Wayne, and give me your size, and the size is if you want to get 2. And you're going to get 2 T-shirts for that, man. Thank you. Fantastic. Really cool. This is why we got beautiful people here. And you know, you guys know I don't make any money on this. I'm not taking any money for any of this. I'm just interested in getting this stuff out there. You know. Yeah. Thanks, Bob, for thanking Wayne. Isn't that cool? Yeah. Wayne's very much into astronomy. I mean, he's really cool that way. You know. And I was tickled pink to find out that he lives literally about 2 miles here from here. Yeah, he's been here to the house. He came up with a T-shirt that time. Yeah. Yeah, you meet really cool people, really good people. He's one of them. Okay, fit the height. Let's redock this. There we go. Look at that, guys. That's really pretty. We're going to go to 20 at 45 seconds. That'll give us a total of 14 minutes. Well, actually, a little bit more. Okay, see that, Marianne? He wants 2 shirts, 1 medium and 1 2X. Here we go. 20. Wayne, you got it, brother. You got it. The only caveat is you've got to send us a picture of you in the shirt. Only if you want to. That's really cool, though. Yeah, it all goes to the maintenance of the scopes. You're right, Marianne. Okay, we're good now. So we did this, took that, and now we'll go to the next guy. All right, so this is neat. Now, this is a very extensive object, you know. And this is, again, these are all in our galaxy. These are all in our island universe of stars. But there's other island universes out there of stars. We leave behind our stars, and we end up seeing other galaxies. If I zoom out here, you can see the band right here. This is the band of the winter Milky Way. We're looking basically away from the center of our galaxy, looking at the outer spiral arms that are beyond us. All right, and we're in it, which is really amazing. So what we'll do now is move our way over a little more. I want to come over here. And there's Leo right there. Leo's pretty high now, and I want to get an image of. We did a couple of these other galaxies last time, but I'm gonna do the Hamburger Galaxy tonight. This is cool, and it's gonna take a little finesse because there's very few stars to guide on in this region, but we're gonna see what happens. All right, our guider is complaining because it can't see anything, and of course it can't. All right. Okay, so it says we're on the Hamburger Galaxy. The question is, are we? Well, let's do this. Let's do a quick 10-second shot to do this here. Wayne, you see that message? Marianne says she's going to send out the shirts when she gets back on Sunday. Marianne, we have a medium. We have mediums left. Oh, hold on. This looks like it right here. Not sure if that's it. I thought it was. Hold on, let me actually see if this will work. Michael Hendricks says the Hamburger Galaxy is one of my favorites. Okay, so that's IC 2745. Okay, thanks, Marianne, for answering that. IC 2745. Zumbo in here, and let's see. All right, let's find out where IC 2745 is. Actually, since we have that there, let's center that in the view. We're not going to take a picture of it. We're just going to center it in the view. So it's a 10-second exposure, so it's going to take a bit to come in. That's all right. Okay, so now IC 2745. Let's find that and see where that is. IC 2745. Okay, so we're close. All right, so that's good. So I'm going to just say we're almost there. And now what we'll do is move up to the Hamburglar. This guy. All right, so up we go. And there it is, right there. Okay, good. It was that close. Look at that. Okay, let's do this. There it is. And that is going to be the galaxy that we want to see. That is the Hamburger Galaxy. So we're going to call that Hamburger Galaxy. And it should be good. All right. So there we go. And now what we're going to do is we're going to come out of here. This one is going to be a little different. We're going to, first of all, make sure we have a guide star. Let's go grab a frame and drop that down. See, very few guide stars. This area is, I might have to maybe do a little longer exposure. Let's try that. Let's try that. Okay, let's see if we can find a guide star. That's funny, it found the one I thought it might find. Okay, this is a very, very difficult view, but we're going to do it. Hopefully we won't lose the guiding. So this is going to be a 60-second shot. Okay, and away we go. So you can see this dark lane across the center. All right, now we saw red giants. We saw that the red giants actually can make lots of dust when they're large, and they just slough off this outer dust. We've seen planetary nebulae, the results of the death of a star like the sun. We've seen the future death of stars that are much more massive and hot than the sun, the Wolf-Rayet stars, like at Thor's helmet, and it blows off its outer layers violently. And then we see nebulae that are stellar nurseries making stars. And we talk about, when you look at Thor's helmet, for instance, you see all this dark dust intertwined. in the Seagull Nebula. See this dark dust. We're looking at dust in the middle of the dark lanes of our galaxy. The spiral arms have these dark lanes of dust. And we see that in many galaxies, like right here. This is a dark lane of dust in this distant galaxy that we're looking at right here. All right? And that dark lane of dust, and the picture came in just in time, we're looking at it almost edge on. So we're seeing that big, thick, dark lane of dust through the middle of the galaxy. All right? And we're going to go into the stack now and do this. And that guiding worked fine. So we're going to get another one coming up. So it's really something. And now let's just wait for this to come in. We have going about 15 seconds or so. And Ron Regier is here. Hey, Ron. Today is his wife Dar's birthday. Happy birthday, Dar. We'd all sing happy birthday, but it would probably come out at all different keys. Look at that. Wow. There you can see that. That's beautiful. This is going to be a really nice photo. And so I do want to thank Ron. Ron taught me a lot about petroglyphs. He's an expert on indigenous petroglyphs. And I did a talk called Drawn in Stone, talking about pictographs and petroglyphs, and Ron was in the audience, and I really appreciated that he was there. So it was nice to see him here, and that's really cool. Kevin O'Neill is here. Nice to see you, Kevin. Thanks for coming. Yeah, and then oh, Ron, by the way, my best to Dar, your wife, of course. And I know I keep saying it, but I do want to make it up to Rimrock, where you are in Arizona. It's a really beautiful location. Really, really beautiful. Man, look at the blue here. You guys can see the central bulge of the galaxy is has a lot of yellow stars in here. But then outside here, you see all this blue. There's a lot of young stars. Now, if we looked at this from the top, we'd see spiral arms, okay, probably. But they seem to be warped. And it could be because this galaxy might be interacting with the other two culprits in the Leo triplet, which are in this region as well. And if we look here, you'll see them, okay. We have the Leo triplet here consists of this galaxy, this one, which is, okay, this is a Messier 65, this is Messier 66, okay? And so these two galaxies may have something to do with the warped nature of this one. They may be gravitationally interacting. So this one is 35 million light years away. This one is, let's see what its distance is. Sorry, they don't show a distance. It's about the same. But then this guy, okay, the Hamburger Galaxy, this one is, and I have to try and get it without hitting the plus, or my thing there. Yeah, there it is. This galaxy, right, its distance is 45 million light years away. So a distance of 10 million light years for galaxies this size doesn't mean a whole lot. They are gravitationally tugging on each other, and this galaxy may have been closer to those galaxies and passed it. And when it did, it might have been skewed so that material was pulled down and away from it, like we're seeing several lanes here that look like they've been split. And we could be looking at a spiral arm that had dark lanes is now lower. So the galaxy goes like this, but you have one spiral arm in the galaxy that's actually has a warp in it. And that could be what we're looking at right here. We only ever see it from the edge. We can never see it from above. That was pretty cool. And Tamara Mama asked a question. By the way, thank you for coming into the chat, Tamara Mama. The telescope I'm using, it's right there. It's an 11-inch Celestron with some special filters that I've put on it, so we can actually showcase some of these details. The area there, the sky is exceedingly dark, and so it's just beautiful there in Benson, Arizona. We're on a mountaintop with 10 other astronomers, and we have one of the buildings up there. And we may have another telescope in here soon. We're going to definitely have one piggyback on this eventually. So we're trying to build up our capabilities to do real science as well. I'm an astronomer. That's what I got my degree in. And so I went to the public outreach side of things. I wanted to bring people into the conversation, tell them all about, unidentified flying objects and alien life capabilities and possibilities in the universe. And I talk about it in terms of, life in our galaxy versus life in other galaxies, like this one right here. Okay? And it's really just one of these things where we spend a great deal of time sharing astronomical imagery and what we do. And by the way, every photo we take is available for you to take down free from skytourlive.org. No catch, no nothing. If you want to contribute, you can join our Patreon. If you want to do a one-time donation, you can. You don't have to. It's nice that people do. And the bottom line for us is that we're here because of your assistance. Without it, we couldn't do this. The Patreon's very helpful because people join us for $10 a month. That's like a reasonable donation, sure. So it's $5 a month, and then we have people that are all above, all throughout the spectrum. It's just cool, But I'm glad you asked the question, Tamara, and thank you so much for that. And if you haven't yet, do click the like and subscribe to us, and then find out when we do this. We do this on many many dark nights, and we have over 550 of these types of sessions all up on our channel on YouTube already, and that's Sky Tour Livestream with Mark D'Antonio. If you look up Sky Tour Livestream, you'll find it on YouTube. And click the bell and select all notifications so you get it. Benjamin says, I always tell my friends and coworkers about your stream and think that I'm crazy. I'm like, here's a link. Join and listen. Yeah, that's right. It's cool. Yeah. Yeah, and then, of course, people say you're just looking at little lights when you look in the sky. They don't realize sometimes you're looking at stars that are so much bigger than our sun that if you put it where the sun is, it would all swallow up Mercury, Venus, Earth, Mars, and sometimes Jupiter. That's how big some of these stars are. Unbelievable. Yep. All right, so we have 8 done here. Look at this beautiful view of this galaxy, the Hamburger Galaxy. Really, really nice. Oh, yeah, thanks, Bob. And yeah, if you ever watch History Channel, you can see me on many of the episodes of The Proof Is Out There. I was in the NASA's Unexplained Files series, What on Earth series, CNN, Netflix, Discovery Plus, Discovery, on different shows. And I think that's a fun thing that I do. I like to do that. In fact, this Friday, which is what, tomorrow? Yeah, it's already tomorrow because today's Thursday now. History Channel's here, and we're filming season 6 of proof is out there. All right, so I've got like 10 different stories to do for that particular season. So that's good. It's nice. And they've used me for all 6 seasons so far, so that's been kind of cool. They also had me down there in New York City, actually. They come here when they have to do this. But they had me down in New York City to do a sizzle reel for a new series. The sizzle reel is one where they try to sell it. And they're going to sell this series. And hopefully, if they do, then I'll be part of that too. You know, and I get the word out even more. You know. And you know what? There's no ego here. You know, I mean, this is, you know, somebody has to say it, right? Somebody has to say this stuff. If it's me, that's fine. If not, that's also fine. Okay, let's drag that over just a little more. Look at that. This is perhaps one of the best views of the Hamburger Galaxy we've ever done. You can see the outer extents very nicely. The disturbed outer extents. This is only 10 images. Now, here's the thing about the digital noise. When you zoom in on this, you'll see something. See how grainy this gets? Okay, that's pretty grainy. You say, oh, that's nasty looking. That's no good. All right, I'm going to tell you about this red patch, by the way, in just a minute. But there's that red, that beautiful dark lane of dust. Well, here's the problem. That noise is random noise that's induced by the sensor being at 200 gain, okay, for 60 seconds. Now, the thing that's important to understand is we've got 11 photos here. And so with 11 photos, you have half the noise that you did when you had 5.5 photos. Okay? So effectively, that's how that works. So if you double the photos, you have the noise, that digital noise. So the more photos you take and stack. Now, what do I mean by stack? We take an image, take a second image, align it with the first, and lay it on top. We make an image sandwich. As you make that image sandwich, the overall result is that the randomized nature of this stuff out here will randomize to something smooth. And only the data that means something will be coming through at that point. So I've done 12 shots. If I do 60 shots, this is going to look even more smooth. However, I'm not going to make you sit through that. We're probably going to go to 15 shots, and then we're going to quit with this object. So that's just something that allows us to make use of our data in the best way possible, you know. So if I do this here and I say fit the height, a little smaller, look at that, now you can see it. Now let's put that down and enlarge this. Oh yeah. And you can see where the telescope's pointing. It's actually pointing pretty high up in the sky. Our guiding is doing well. We have this guiding system going in the background here. And it's staying right on the money with a 2-second exposure. Not bad. No failures. Okay, so we've got 13 stacked. So yeah, this is good stuff. Good stuff, guys. I just want you guys to know I really appreciate you coming out to view these things. You know, I don't care if I'm streaming to one person or 1,000 people. You know, I really just enjoy showing the universe to everybody. Some of you might remember this. We were streaming the lunar eclipse of January 2019, and the moon was blood red, and all of a sudden we saw a white flash on the moon. Little did we know that we were one of only 5 people on the entire planet to capture a meteor striking the moon right in the middle of the eclipse. And it hit right in the red zone on the moon, in the red shadow. Well, obviously the moon is struck by meteors a lot still, but seeing them, that's the part that's really the trick. So if we observe the moon all the time and just the moon, we'd see a meteor hit for sure. So it's pretty cool how that happens. Yeah, that's right, Bob. The smart people are here. Ronald remembers it. Ronald, ERT Radio. Check out his Mixler, right, Ronald? ERT Radio. Radio. Okay, I was going to tell you about this red. All right, so what's going on here is this. This galaxy seems to have a red area in here. What is that? Well, some galaxies, after interacting with other galaxies, we had a moth fly over the camera. After interacting with some galaxies, they will actually cause star formation to really, really pile up in these galaxies. And in this particular case, this may be one of those regions. So when we zoom in on this, you can see that it's red. It's red for the reason we were thinking. This is a massive stellar nursery region in this galaxy that's 45 million light years away. You know? Absolutely crazy. So, by the way, 45 million years ago, when this light left, the light that we're watching right now build up on our sensor, when this light left, it was the middle of the Eocene epoch here on the planet. It was a greenhouse world. There was no ice at the North or the South Pole. And the jungles literally stretched all the way up into the Arctic Circle. Okay, so it was a hothouse world, a real hothouse world. Okay, the map would look kind of familiar to you, but it was off in a lot of ways. There was water in some places that there's no water now. Florida would look very different. At the time, India was colliding with the Indian tectonic plate was colliding with the Asian plate, and that forced up the Himalaya mountains, as we have heard in the past. And separating Africa, Europe, and Asia was a giant sea called the Tethys Sea, and that was still there at that time. Again, tectonic plate movement causes all these changes. And what we call the Mediterranean Sea now was much, much larger, stretching deep into Central Asia at the time. Okay, so that was pretty cool. Now, Antarctica was green. There was no ice. Antarctica was a green region of the Earth, and it was warm. And it only recently at that point had begun to split apart, but Antarctica was still a lush forested continent, and not the frozen wasteland that we see today. And that's when the light left this object that we're seeing right here tonight. When the light left, all those things were happening. Incidentally, at that time, it was the golden age of mammals. Okay, so the first larger mammals began to show up in the shallow Tethys Sea that I just mentioned. In the ancestors of whales were there. The Basilosaurus, for instance, was there, elongated predatory whale, but it had tiny vestigial hind legs. Primates were small lemur-like primates that were swinging through the trees that covered both North and South America and all of Europe. So a lot going on there at that time. So that's what was happening here on Earth. Now, the carbon dioxide levels at that time were significantly higher, approximately 2 to 3 times higher than they are now. So we had trapped ice, which prevented trapped heat, which prevented ice at the poles entirely. So that's something to think about for when the light that we're seeing tonight left this object. Right. So isn't that interesting? The actual global temperature was, let's see, the average temperature was between 18 and 27 Fahrenheit, which is warmer than the modern era. I know that sounds like it's frigid cold, but that's an average temperature, which takes into account the cold and the hot. So if it was during a hot house world, an average of 18 to 27 means that the world was pretty warm. Okay, that's again an average. In the equator, the temperature soared well above 100 degrees all the time, every day, and it was humid. Right, lots of moisture, lots of water. So lots going on. All right, so that's this object. Now you can see the dark lane in here showing detail. You can see kind of through the dark at the red object in there. Let's see if we can coax any more detail out of this. Let's try that. Yeah, that kind of looks interesting. Let's our curves look pretty well lined up, but let's see if we can do a tiny bit of a jog motion here. Get rid of yeah, there we go. Wow, that is something. So this is looking very different from we've ever seen. This is the best so far. I'm only doing a 60-second exposure because I've got you watching. If you weren't here, I might do a 5-minute exposure of this, and make 50 exposures. So that's 250 minutes. That's a long time, man. I don't want you to have to sit through that. Let's see what's going on here. Okay. Let's see now. I'm trying to see. Okay, Westwind 3, welcome. Nice to see you. I'm glad you joined us. Make sure you like and subscribe. Help us with that, man. Subscription's free, of course, and the data we give you, these photographs were taken too. So it's neat. And yes, it's totally live. I'm in Connecticut in the United States, and the telescope is in Benson, Arizona. We've got another one in the Sonoran Desert out in Arizona. This one is a magnified view, and the Sonoran-based telescope's a wide field view. We're not running the wide field view right now, but we do have two. And we're going to add to the list of telescopes that are in this one as well soon. Thanks, man. Thanks, Westwind. Thanks for joining us. We have 550 streams up there, including the one where we caught the meteor striking the moon. And we do comets. We look at comets. 3i Atlas we have up there. Tons of 3i Atlas streams that we've done. I've done a bunch of 3i Atlas stuff, actually. Coming up, I'll be doing that for Proof is Out There on Friday for history. And actually, you guys may remember the animated file showing 3i Atlas moving through the sky that I did. Well, that's going to be on History Channel. They're using that as what they call an asset. They're going to actually use that as part of the story. So that'd be kind of cool. It'd be nice to have my stuff up there. Neat. This is looking better. See, as we do more photos, guys, right now we're up to 24 stacked. As we do more photos, you start to see details in here emerging that we just didn't see before. All the complexity in here. Let me do one thing. Let me turn off all the enhancement here. Okay. So that's what it looks like without trying to sharpen it up. And this is what it looks like when we sharpen it. You see the difference? You start to see all the detail in here. That's like little tiny pieces off of this. Just stunning. And I'll be able to coax more data out of this as we move. As we do more. Okay, I'm going to dock this back up now. Okay, and then let's make this the actual size for the screen. That's gorgeous. What a beautiful object. Alright, we're going to save that. Save it exactly as seen. There we are. Now I will annotate it. Okay, let's get the annotation to line up. And then we'll save with the annotations. Wow. There we go. That's a beautiful image of that galaxy tonight. So thank you for sitting through that with me. Oh, thank you, Benjamin. All right, let's go on to something else. I'm getting very, here's the thing, everybody who knows me knows that I like to do just one more kind of a thing. And that's kind of what I'm doing. Bob says, wife says it's okay to have a man crush on Mark. That's funny. Well, thanks, man. Thank you for the compliment. That's very kind. And Batman is here. Batman, what's happening, man? How much value is added to the image from a larger mirror? Like, what's the max practical for the mount? Does it change much? That's one of the best questions we've gotten, I'll tell you. Not that the others aren't good, but that one's actually a good one. The larger the mirror, the better the resolving power. So if we did get a bigger mirror, then those tiny details in that galaxy would be more visible clearly. And so we're working on that. We have a possibility of a telescope going into Colorado to make a third telescope system, and this one would be larger and allow us to do exactly the kinds of things that you're mentioning. So we'll see about that, but we're working on it. And like I said, hopefully, I don't have hundreds of Patreon people. I just have a handful. The more we get, the better it is, obviously. So the sooner the better we can do some of these really cool things. All right, I'm going to pull out of this. This is where we were in the constellation Leo. And let's look up high here and see. We've got Ursa Major up there. All right, and so with Ursa Major being way up there, there's another galaxy that might... Oh, well, actually, we might want to look at this too. Yeah, the Owl. Okay, and then this galaxy, the Vacuum Cleaner Galaxy. Yeah, I know, dumb name. But right near the Owl, we also have the Surfboard Galaxy, which is really cool. But let's do this. Let's go to the Owl. I'll tell you why. The Owl Galaxy is fascinating because... Owl Planetary Nebula, the Owl Nebula, because this is another stellar death nebula. And the telescope's going to spin around to get up to it. So you're going to watch it go do its thing. It's going to take it a bit. I mean, when you've got several hundred pounds of stuff, you want to move it around. But there it is. It's right there. See it? Can't miss it. All right. Maybe you can. All right. What we're going to do now is we're going to grab this. I'm going to show you this. This is another example of a planetary nebula, a star much like the sun. when it dies, is going to do what we see here. Okay, we're going to see it do what this is doing. It's going to slough off the outer layers. This one is a lot more regular. This one, it's like a sphere, but it came off at again, the star was spinning and it came off sort of differentially, so you got some odd shapes. But they're symmetric on each side, which tells you that we're looking at an object that was created, again, in 3 dimensions by a star that was spinning. And you'll see exactly what that looks like. There's a lot of oxygen, which is teal blue in this. There's a lot of hydrogen emission, which is red, which you'll see some of that too. It's not as prevalent as the oxygen, though. Okay. Well, there it is. Now, that doesn't look like much yet because we've got this on overdrive. We've cut that down, and you can see we have some noise, but that's going to get mitigated very quickly as we start to get more images. We only have one now. When we get a second one in just 10 seconds, this noise gets cut in half, so this will start to look twice as good, as you see here. So let's see if we can catch that. So here it comes. We're 2 seconds away. Watch the nebula. All right? See that? See how that changed? And detail in the nebula is now showing up a little better. This is the Owl Nebula, so called because these 2 little dark spots, as we progress, will look like an owl, like a barn owl. Okay? That blue star, that's a white dwarf. Again, the size of the Earth. Our sun will be the size of the Earth. Now, the Earth is way smaller than the sun, which is 865,000 miles across. But after the sun ejects its outer layers, which will likely swallow up, will swallow up Mercury, Venus, well, the whole solar system eventually, the white dwarf is going to shrink and will end up being Earth-sized. That's the core of the star, which right now is still many, many tens of thousands of miles across. Okay, but that core of the star is going to shrink down to just about 8,000 miles across. So it's going to be very dense, very hot, and it's going to give off a lot of ultraviolet radiation, which is going to cause any of the gas in the ejected gases from the original star to glow. And we're seeing that the oxygen is glowing here. Let me, I still have to fix this because we were way past the curve here. Let me do it this way. Let's put it where it wants to go. Okay, and now let's color correct. All right. So now we're seeing this like we expect to see it, right? This is the Owl Nebula. There is the really, really hot blue white dwarf in the center. Now let's get a distance to this. I forget how far this is away. Distance is 2,025 light years. Okay. So at 2,025 light years away, obviously, here on Earth, the date when the light left the object that reached us was actually 2 AD. Okay, the second year AD. And the Roman Empire was Augustine, the first emperor of Rome. And the Mediterranean world was experiencing relative peace at the time. There wasn't a lot of stuff going on, a lot of building up of infrastructure. Romans were perfecting the use of concrete back then, unknown previously. And this was the era when the great Roman aqueducts were built. When the light we're seeing right now, leaving this, left, the Romans were building aqueducts here on Earth. And this is 2,000 light years away. Yep. So a lot was happening, in China it was the Han Dynasty, And we also had the city of the gods, Teotihuacan, was rapidly growing at this time. The massive pyramid of the sun was actually under construction, or had just recently been completed by then. So a lot going on there. In Guatemala and the Yucatan, the Maya were building massive stone complexes, and were literally at the top of their game, you know. So a lot going on. So you see, that's what was happening here on Earth when the light we're seeing tonight left that object. I hope you don't mind those perspectives. I hope you, it helps you see the incredible distances that are in the universe. Okay, Benjamin asks a really good question. He asks, if I was floating directly in front of this galaxy, well, this isn't a galaxy. I think you might have asked the question, we're looking at the other galaxy. Would you see its color? You know what? With your small, tiny eye, which is only 7 millimeters across, that's the size of your telescope. It's 7 millimeters, 1 power, effectively. So, that's not a lot of light gathering power. So you probably wouldn't see any color. You might just see a hazy thing in the sky. Kind of like when you look at the Milky Way under a dark sky. You just see like the cloudy Milky Way with your eye. But a camera shows you the most extensive, beautiful, most unimaginable beauty that you've ever seen. This is the owl. Set the target name and save the image. Okay, we have 12. We're going to save this. Save exactly a scene. Okay, so you can see this little edge of hydrogen down here. Let's see if we can get a little more data out of this. And let's do this. Okay, so you can see there's a core shell of a darker oxygen emission and an outer shell of a lighter oxygen emission mixed with hydrogen. See that? This is a very subtle feature not often seen, but we're seeing it here. Michael Hedrick, thank you. Oh, Westwind says I greatly enjoy the narration. Okay, cool. I'm glad. I mean, I have a presentation planned for Roswell in July, where I'm going to be talking about interdimensional travel. But I have another presentation for Contact in the Desert in May, where I'm going to be talking about historical perspectives on Earth as seen from the objects that we're catching the light from tonight, kind of like this. Like what I'm telling you, I do in a presentation with images that we've taken. Yeah. So you don't want to be anywhere near this. Because if you were anywhere near this, you would be fried, because the ultraviolet radiation coming from these white dwarfs is exorbitant. It's huge. Hey, Gary's with us. Pop Culture Minefield. What's up, brother? Wow. You gotta understand. Gary is a famous illustrator. This guy. You see him down there? Okay. Guy's a famous illustrator. This man is just incredible. And I've had the privilege of being on shows that he's part of. And I gotta say, really, really talented guy. Really talented. You know what I didn't tell you ever, Gary? I don't think. When I was working years and years ago in an insurance company, I actually created a newsletter for them. But I was actually creating comics, making comic strips and writing comic strips that included what we did in the insurance industry, because I felt it was so boring as heck. I just could not. I could just not, tolerate it. So when I was doing this newsletter, I added comics and cartoons, and they were very well received. And of course, the stuffy headed people in the company were like, "Well, that's not very business professional." Yeah, okay, fine. Yeah, check him out. Check him out, guys. Thanks, Bob, putting his link up. Thanks a lot. I'm glad you could join us there, Gary. I haven't talked to you for a while. Yeah. I celebrate everybody that has some do this cool stuff. So. Want to take a ride? Please, Mr. Spaceman. That's good. Spacer Man. Oh, Spaceman. Yeah, that's cool. Uberku says that Westwind says he's a big fan of Art Bell from decades ago. Yeah, me too. From the high deserts of Pahrump, Nevada. Remember that? And I've been on Coast to Coast about 4 times now. And I've been on with George Norrie, Connie Willis, and other people. It's different from when it was Art Bell. But I will say that it's exciting anyway to be part of that. I need to know if the aliens have space weed. I've got you probably can't handle theirs, I'll tell you that. That's funny. Okay, let's we got 22. We're gonna save here. And come out of here. Alright, so this image is up there for you to take and enjoy. It'll be there momentarily. Oh yes, west of the Rockies. Yeah, he said that. That is absolutely right. The guy doing Coast to Coast now is George Norrie. And they flew me to Boulder, Colorado to do a one-on-one with him. And then they had me on the Coast to Coast radio show like maybe 3 or 4 times so far. So it's kind of fun. I just did it maybe a month and a half ago. I was just on. And that was fun. It's always fun, but it's always late. I mean, I'm in Connecticut, so they're West Coast times, and they're from like midnight. So I'm up in the middle of the night for these shows. Gary says, just saw you. Latest episode of Proof is out there. You were on. Need you on more. Damn it. Well, this next season won't disappoint you then, Gary, because I may be in most of the episodes this next season here. That's neat. It's all cool, Also, by the way, some of you know the story. I was on a submarine as a guest years ago, not as a sailor, but as a civilian contractor. And that submarine, we're going to go right to the surfboard and try that. No, wait, I got a better idea. That submarine was actually basically I'm saying that submarine was basically being tracked by an interesting object. That object was what's called a USO, unknown submerged object, and this thing was seen in the sonar. It was captured on sonar. It went through the sonar at several hundred miles per hour. Okay, and they didn't know what it was. They had no idea, and I can totally get that. I totally understand. No idea what it was. But boy, oh boy, that was crazy. I did a job a couple years later for the Joint Chiefs. They worked directly for the president, and I was doing a physical model of submarine technology because that was my specialty, still is, in the submarine arena. Inner space, outer space. Here, not so much. And in the inner space realm, I have some technology background that they like, and they let me go out on a submarine. I can't say why or where, but the thing was interesting was I ended up. I'm going to do this here for a second. Let's go 10 seconds. I ended up on a boat in the middle of the Atlantic Ocean. Seasick as heck because it was a boat that their submarines are like sewer pipes with end caps. So I was rocking and rolling in this boat. There it is. And the rock and rolling that I was doing was just, it was maddeningly bad. It was horrible. And so in order to get my stomach to settle down, I actually went over and sat next to this guy who was doing the sonar. And I just figured there's some action going on over here, so I might as well just, hang out over here. So I did, and while I was there, they actually had something zip through the sonar at hundreds of miles an hour, and they called it a fast mover on the submarine. So a couple of years later, I was doing a job for the Joint Chiefs. I went down to Washington, delivered my project, then had a meeting with one of the chiefs, and I asked him, what can you tell me about these fast mover things? And he looked at me and said, I'm sorry, Mark, I can't talk about that. Wow. So by saying nothing, he told me everything. It was crazy. So they do exist, in other words. And our Navy's official policy is observe, report, do not engage. And the reason is they can't. They can't engage. They don't know how to engage. I'm just placing it. I'm getting the placement of the galaxy here. I think the center of the galaxy is like right here. I want to show like the area out here. Let's see if it shows here. Oh, the galaxy's down there. There it is. Okay. So let me do this. Let's say this. Good. Now we're going to take that. We're going to move it to the center. And let's make sure that I still have everything here. Excellent. It'll all be there. Good. We're going to set the target name and get out. Look at all the things in this galaxy. See, that's what happens. Sometimes we see other objects in another galaxy and we make them and we view them as strange objects in a different galaxy as well, which is kind of cool. So we're going to see this beautiful what's called OB association, hot O and hot B stars. This one too. So what we'll do here is we're going to make this a 55-second shot. This is the Pinwheel Galaxy. This is going to be a beautiful view of the galaxy. Look how high up our telescope's looking. That's actually pretty good. All right. Let's go into our live stack here. And we'll go into our deep sky mode. This is neat. Wow, it's 1 a.m. Phew. Might have to make this the last object. Let's see here. Westwind says George Norrie is nice. Kind of puts me to sleep. Me too. You're not the only one. Yeah, George is interesting. Oh, you know what? It would have been nice if I started guiding, huh? Yeah, but there's the galaxy. You're going to see some really cool spiral arms from the top. So we've seen spiral arms, galaxies from the edge with the dust. Now you're going to see what that same type of thing looks like from above. Okay, so to do that, we're first going to go and grab a image. All right. And after we grab the image, let's go over here, bring that up a little brighter. Grab our stars. We're going to, oh yes, that's a perfect star. Beautiful shape curve. Nice. Okay. Now what we'll do is clear this just in time for the new one to come in. That looks perfect. Oh, it may not though. Oh, not bad. Good, we lucked out. Alright, so this is called the Pinwheel Galaxy. And it's a beautiful galaxy, and we'll talk about its distance here in just a minute. I gotta look and see how far away this was. I can't remember how many millions of light years. Okay, this one is 20 million light years. So when we look at it, we say, how long ago did the light leave this galaxy? Well, it left it 20 million years ago. And this is the age here on the planet where the biggest change that occurred wasn't in the sky or the water, but was on the ground. And this was the Great Grassland Expansion. This is where grasslands began to dominate the planet. You know, they had, you know, plants before, some minor plants, and they began to take over the planet at that point. But as the climate got cooler and drier, and the rainforests retreated, they were replaced by these vast open savannas and grassland. And that's the kind of thing that was going on back when this galaxy's light that you're seeing right now left this galaxy. Okay. The Himalayan mountains were in full swing. The crash of Indian subcontinental plate was in full swing, raising the Himalayan mountains even more so. And what happened was when those extreme heights were reached by the Himalayan mountains, guess what that does? It changed global weather patterns, because the mountains are now sticking up in the air, blocking a wind from crossing or going smoothly over the land. And so global weather patterns changed, you know. Really interesting. So I thought that was interesting how that worked out. All right, let's see, we've got 3 of these here. Let me come in here and let's color correct. Oh yeah, look at that. Beautiful blue arms of the spiral galaxy here. These blue arms, of course, being young hot stars. Look at that. Okay, this is a face-on view. Now, from an edge, we might see an elongated core. I'm sorry, a central nucleus tapering off on the edges. And at the edges, we might see some of this dark dust in profile as we're looking through, right? And so that's why when we see edge-on galaxies, we always see what looks like a dark dust lane, because the galaxies have this beautiful dark dust. Now we're gonna do this. We have 4 captured. I'm gonna do this. Let's drop that down and make this full size so we can actually see what's going on here. Notice that this is blue. Notice that this is blue. This is an area of intense star formation. It's called an OB association. It's an association, as you might guess, of O and B stars. Remember, the hottest and bluest? Okay, O's and B's. And that's what we're seeing here. And then that stuff that we're seeing in here, these are the hot blue stars inside these spiral arms, where star formation usually takes place in galaxies in the spiral arms. The nucleus of the galaxy has the older stars, okay? And you can see this interesting pattern of dark nebula here. You see it? Comes out, goes around, and curls up over there. This is one of those dark lanes. This dark dust, everything you're seeing here, this dark dust was created in the outer atmospheres of supergiant stars. Not necessarily supernova, but outer atmospheres of these giant, supergiant red giant stars. And so you can see from the sheer volume of this stuff here that there must have been an awful lot of these supergiants. And the answer is there were. There were. Okay, Ben says, I have a MUFON report for what I saw with pics. Even had a phone interview, which doesn't mean much. No, it does. When was your sighting, Ben? Just curious. Ronald, this is called Measure 101, otherwise known as the Pinwheel Galaxy. Did I put that in here like that? Let's see. Yeah, I did. Yeah, this is the Pinwheel Galaxy. It's the quintessential Pinwheel Galaxy. Now, we classify galaxies by the tightness of their spirals, okay? Whether they have a elongated bar of material. And here we see multiple spiral arms. In a barred spiral, we tend to see two major spiral arms off the end of each bar, and it goes around. Okay, in this case we don't see that. We see a regular spiral. So this is a regular spiral, and it looks like it's it's not an A where they're tightly wound, or a B where they're more, a little bit looser. It looks more like a C where they're kind of far apart and quite loose. Let me see if I'm right. This galaxy. Okay, it says it's a barred spiral, so I'm going to dispute that. I think this is wrong. This does not look like a barred spiral at all. I think it's an SC. Or in the new format, capital S, capital A, little c. That's what this looks like to me. Maybe a B/C, but I don't see a bar. Batman says, beautiful image you get into how the topology of the universe is flat, even though I'm told it's not in the 3D. Yeah, that's you're right. Hearing flat universe is Euclidean geometry. Yeah, exactly. I don't talk much about that because all that will do is make people still think it's flat, and then they'll say, "Oh, flat Earth." And nothing could be further from the truth, of course, as you know. But I don't typically mention that. No, I will if there's a call for it at some point. I mean, you're asking a little bit, but it would take a long time to set it up to understand it. And I at this point at 1:18 in the morning is probably not the best time to do it. I probably should do it when galaxy season is in full swing, and this is much higher in the sky. We can bring it up and talk about it, and mention the geometries and the different models for the universe like that, because that's really very important to understand. And I really appreciate that question, Batman. Thank you. Earth Radio, Mark, do you know how long it takes for the sun to get over the mountain range after the sunrise and the other side of Benson? No, I don't, Ronald. But you know what? The bottom line is, it's going to vary based on your season, because the Earth, member, is tilted because it's on its tilted axis. So, you figured it out. Okay, good. Yeah. So you can go ask an AI program or something if you want to. It'll probably tell you. Oh, Daisy and Zoe. apologies, we have to early appointment tomorrow. Oh, Dave, it's okay. It's okay because you can go. Of course you can. I get it. I had to start later because we had to set the clocks an hour. I lost an hour, so I don't start at 9 anymore, and I have to start at 10. And it's already 1 in the morning here. It would only be just after 12. So, arg. But it was great to have you here for the time you came. So thank you so much for coming. And you're always welcome. All right, let's do this. Let's see where it wants to put its processing. Yeah, not too far away. Okay, not too far. That's beautiful. Okay. Do that. And I'm going to do this. I'm actually going to drop this down a little bit. Yeah, and here's the reason why I'm doing that. Now, you can actually see some of the details inside this galaxy. Look at this beautiful OB association now. Okay, we've stacked 12 images. This one's beautiful as well. In the outskirts. Now, if this was our galaxy, okay, where would we be? We'd be right about here. Okay, we're actually a little closer than we thought. We used to think we were like 2/3 of the way out. We're actually a little bit closer. We're like about here. Okay, really cool. Fred Phonebone has a question. Are all the spiral arms basically the same plane? It seems like the one on top is sort of behind the other one below it. Oh, that doesn't have to be true. In the last image, Fred, when we looked at the hamburger galaxy, you saw how the dark lanes were horizontal, but then you had one that was sort of split off below. That's an example of one where the spiral arm that this dark lane is in, because the dark lanes follow the spiral arms, that dark lane was warped downward because of gravitational interaction with another galaxy. So in this particular case, though, this galaxy seems to be pretty cohesive. It doesn't look like there's a warp. Now we could tell that by looking at how fast the neutral hydrogen is heading away from us or heading toward us. Okay, that would be a good help for us. We could look at that. That's how we study that kind of thing in galactic rotation. So, however, I would say that the galaxy that does show that very, very clearly is the Whirlpool galaxy. On the next stream, we'll show the Whirlpool. And the Whirlpool is a little smaller than this one. This is a beautiful screen-filling galaxy. And the Whirlpool galaxy actually was interacting with other galaxies, one that is still seen in it. You have a spiral, and you have another galaxy literally attached to it. All right? And this, one of the spiral arms of the Whirlpool is pulled down so that when you actually look at it from the top, it looks like this. Okay? With this spiral arm reaching toward this here. But if you turn it to the side, okay, it looks like this. With this galaxy being through it, and the spiral arm is, the spiral arm, let me do it this way. The spiral arm is down, it's curved downward. So it's going into the page a little bit. And we definitely have a warp there. Really, really cool. So, Ben says, thanks to the stream, Mark, damn work gets in the way of my earthly problems. I'm sorry, man. But hey, thanks for coming, guys. This will be the last object, so you guys get to go to bed now. And so do I. Shh, don't tell anybody. Earth Radio asks, how long did it take to get to this shape? That's a really interesting question. And going with the other question about the topology of the universe being flat and so forth, that would be a good time to also discuss some of the theories about galactic formation. All right? Because galaxy formation, when we look at this galaxy, if you think of it as a spinning pinwheel, and it is, you might say, hey, this spinning pinwheel, it looks like it's spinning faster in the middle, and that this stuff's getting dragged out as it winds up. Okay? Well, that is kind of happening. However, the stuff on the outside is moving much faster than it should be. If it was following the same physics that our solar system is following, Mercury goes around the sun in 88 days, but Pluto takes over 200 years to go around the sun, right? So the farther things are, they should just be able to lag way behind, because they don't have to be moving very fast to stay in orbit. So how come when we look at galaxies, we find that the spiral arms don't really wind up that much as expected? And in fact, the objects out here are moving faster than they should. The reason is one of another concept that we'll talk about on the next stream possibly, and that's one called dark matter. Not dark energy, that's something else. Dark matter. Dark energy is why the universe is bigger than we thought. Dark matter is why the galaxies seem to rotate like semi-rigid disks. There's a halo around all galaxies of this additional matter that we cannot detect. Just can't. And that data that's there, that stupid, that rotational mass that's helping the galaxy rotate, is something we just can't figure out. So we're calling it dark because we don't know what it is. And it's dark matter because it's different from the matter we're used to seeing. All the matter you're looking at right here, this is called baryonic matter. You know, protons, electrons, muons, gluons, and so on. Okay? That's the regular matter that we understand. But there's matter we don't understand, and that's dark matter. Now, is there possibly a different explanation? Yeah. But we haven't figured that out yet. We don't know that yet. So dark matter is all we've got for now, just like dark energy is all we have for now. Dark energy came about for another reason, and that was because dark energy had to be invoked to explain a phenomenon we noticed with the universe, and that is that it looks like the universe is expanding outward. We knew that, okay? In fact, Hubble came up with a famous Hubble constant, and he calculated the expansion rate of the universe. But it was a constant, but it's not constant. It's changing. And we're noticing that the universe is actually accelerating in its expansion. It's actually accelerating outward rather than just going out at a constant rate. At the beginning of an explosion, when the explosion first takes place, all the matter is exploding outward at a high rate of speed, then it slows down. Well, we're still accelerating out at a high rate of speed from 13.8 billion years ago. So, that tells us that we've got something wrong with our understanding of the universe. Yes, it's 13.8 billion years old. However, it looks like it's still in the acceleration phase of the explosion. How do we explain this? Well, because this sets at odds a whole bunch of belief systems about the universe. What it means to me is that the expansion rate of the universe has to be accelerated by something in terms of cosmology. With the cosmologists who study the topology of how the universe was built, they have to look at this and say, well, the universe was built in a way where it exploded from the Big Bang, and that was 13.8 billion years ago. Now, my idea, which may bear fruit, is that we're in the accelerated explosion part of the phase. In other words, we're still in the early stages of the expansion of this universe. Okay? That's my idea. But the cosmology idea says, actually, there's a dark energy that's actually propelling things away from every other thing. Now, a model I made for that is a very simple one. You can do it too. You get a balloon, blow it up until it's about the size of your fist, and take a Sharpie and put black dots all over it. Okay? Then you blow it up and you watch every single black dot is moving away from every other single dot on there. So they're all moving away from each other. That's a model for the expansion of the universe, because we saw that everything is moving away from everything else at a global scale. On a local scale, galaxy clusters are interacting and sliding around and orbiting each other. That's different. But on a global scale, every one of those galaxy clusters is moving away from every other galaxy cluster. Okay? So our galaxy cluster that we're locally in, it's like 30 plus members in it. And they're all tied together gravitationally, swirling around each other. Andromeda's heading right for us. It really is. It'll hit us in about 4 billion years. But then beyond that, we have other clusters of galaxies, and they're all moving away from each other. Now, the only way they can explain that, in the model I showed you on the balloon, okay, if you blow up the balloon, you expand the balloon, every black dot is moving away from every other black dot. That explains the visual of how it's happening. But it's also, you got to keep in mind that's happening in 3 dimensions too. Oh boy. And that's something else. Okay, that actually leads to some issues. Okay. So trying to figure out what's causing every object to move away from every other object, that's more easy than figuring out why they're accelerating outward faster away from each other. Acceleration means going faster and faster every second. And my theory is that there's no dark energy required here. We're still at the point of the explosion of the Big Bang where things are still moving out at an accelerating rate before they slow down. And they don't really slow down if there's nothing to slow down from. There's nothing to slow it down. It's sort of simple to see. So I do believe that that's what's going on. Now, dark energy, I'm only explaining it and utilizing it because that's a current theory, and I'm okay with that. Current theories are good. However, I can't say for sure that that's exactly what's happening and how it's working. And I tend to think that it's not. But there are some talk, by the way, that dark energy may be going away. So who knows? Maybe they'll come back and say, Mark was right. No, I don't know. But anyway, so that's cool. And we'll talk about spiral structure, where it comes from. We'll talk about topology of the flat universe and so forth, Euclidean geometry. Maybe we'll do that on the next show. That's actually very, very cool topic that's guaranteed to make everybody just leave. I'll have to come up with some examples to show it unequivocally so you can say, oh, that's what it means. So that said, here's the thing, okay? We're looking at Measure 101 here, a flat galaxy, face down, face on. It's really cool to see one like this. And it's really cool to be able to see it with the detail that we're catching it in. Look at these OB associations now. Look at that. Wow. Looking good. All right. Again, if we pull this down, we lose a little of the noise, see? We're not at the point where we can bring this level in as close as I've just had it. We need many more exposures in here so we can actually bring that in and have it be as clear as this. Because this is a good setting for 25 images. 50 images, we might see this kind of noise, which is low, when it's here. Okay, right now we can't. We're seeing, now I have noise reduction algorithms, all that. That's fine. But if the data looks good and pristine from the beginning, then you have less to do, and it's less change to the data. So we'll see what happens. Anyway, I'm going to call it for tonight. It is 1:30 in the morning on the East Coast. 1:30 in the high deserts east of the Rockies. And I'll be talking to you again very soon. Hope you enjoyed it. Let me know. Again, thank you for the donations. That was very cool. Wayne, your t-shirts are going to get out the door. Marianne will deliver them. As soon as she gets back, she'll mail them off to you. Okay? So you have a good night. If you got any questions, you know where to find me. It's at contactskytour@gmail.com. You want the imagery, you know where to find it. It's skytourlive.org. All right. So you guys have a good night, and we will see you later. Look for this image. Before I go, let me just do this so you know I'm doing it. I'm saving that image, and I'm saving it just like we see it. Okay. Good night. Go up, grab it. It's all yours. See you later, everybody.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every